Okay, good to go.
Okay.
So I think we have started and we're live.
Yes. But still, I don't actually have I'm mobile, so it doesn't show all the buttons. It only shows me session and people, and none of the buttons. Okay, there is a YouTube video. Okay.
There is a YouTube video. Where is it? Oh, that's the link.
Okay. No, I think we are not going to live stream, right?
We are live streaming, yes.
We are?
Yeah, we are. Yeah.
Okay.
No one objected, so we will.
Okay.
And I will just stick it on the workshop webpage. Hello, everyone. Sorry, this is the first time we're using this platform for Hope and me as a co-chair. So it's a bit of a learning curve.
Well, we're the people, so.
Okay. Page content. And live streaming. The workshop is streamed live here. Save.
Well, we even have high school student volunteering in Suzhou, from Suzhou.
Oh, that's great. Never too early to start.
Well, it's 4 minutes.
No, I meant to start with functional programming and how the programming will affect.
Oh, yeah. That's.
Oh, so I did add the link, but it doesn't appear on my screen. That's weird.
Okay, so there is a volunteer who. Okay, Martin is the speaker. So and he
Martin
says,
is the speaker. Okay.
He says that nobody can hear me, so we should promote him.
Yeah. So
I'm afraid of how you have to do it because I don't.
I can do it. Let's see. Invite to stage. There you go. So Martin will join us on the stage.
Where do you have these buttons?
If I click the person, then I get a button. Hello, Martin.
Okay, hello.
Hello.
Okay.
That's great. I assume you want to share your screen for your presentation. Is that correct?
Okay. Yeah. Let me try that. Let's see, where is the share screen thing?
It's at the bottom.
Let's actually try to, if everyone actually hears us.
Share screen.
Yeah, just Martin, were you able to hear us when we were talking on the stage before you joined on the stage? Was that okay?
Yeah. I'm just trying to share my screen.
Okay. So people in out there can hear us, right? So good.
Okay. Yep. Okay, so that seems good.
Okay. Good.
Can I annotate this somehow? Are there ways to highlight parts of the slides in this platform? Do you know?
No, I think it's just going forward and backwards. So if you really want to use a cursor, then you're gonna have to share your screen.
I think we're all new here.
Yeah.
Okay.
I did play around with it when I was in one of the demo sessions, but you can't.
I can.
There's
no
pointer
share
or
the screen
anything
as well.
like that.
Let me share the screen. It's fine. Let me try. We still have some.
Yeah. It's all on track.
Okay. No, wait. No, I can't do it.
Is it?
Okay.
Thanks, Tati.
No, okay, let me fall back to the
Slides.
Maybe just okay, let's go the sure way.
Okay, so are you ready? Will you be okay?
Yeah, wait, let me just move this one. Somehow I am on the wrong screen here.
Okay, I'll start with some logistics. Okay, Martin?
Okay.
Okay, so hello everyone. Welcome to this year's Hope. Second year when we are dealing with this new setup for our conferences and workshops. And thank you for coming. Yes, there is still hope. So our first speaker is going to be Martin Odersky, but first a few logistics. This stream is streamed to YouTube as well and recorded. So if you don't want to be recorded, then just stick to the chat and the Q&A, and the session chair will read your question anonymously. Between the sessions, nothing is recorded and streamed, so I'm told. So if you're being shy, you can wait until between the sessions to speak to the speakers. As you can see hopefully as you can see on the conversation tab on the right, you can ask a question in the Q&A, raise your hand. And if you raise your hand, I will invite you to the stage, and then you'll be able to share your audio and video and people can see you. And so we'll see how that goes. And without further ado, let's start our first session. Okay, so Martin, it's with great pleasure to introduce you as our first speaker. Tell us about monads with capabilities, please.
Okay, welcome everyone. Good morning. For those of you who were this morning, like for me, I'm going to talk about some recent work we did on using a really old result by Felinski from 1994 to represent monads with capabilities, and this has essentially very important implications for industrial applications today. So let me go into that. Just see if we can go forward. Yeah. You probably recognize the paper on the left, The Marriage and Effect of Effects in Monads by Philip Wadler and Peter Thiemann. It's probably been one of the most impactful papers over the last 20 years. So much so that now when many people, when they say effect, they mean monad. Maybe not in this workshop. We are more essentially further away. Yeah, we are more. We know better in many cases, but in the industry at large, that's often what it means. There are many use cases of monadic programs. Most of them actually in the domain of reactive and asynchronous programs. So when you have some service somewhere, web service, cloud thing, whatever, it has to process events. And often, if you have people who sort of come from a functional mindset, you use a monad for that, a monad for futures or for tasks, or some super monad that has essentially reader and control and task and error, something like Zio, or I'm sure Haskell has similar monads that do all that. So it goes so far that today often functional programming is perceived as programming in monads in these parts of the industry, which of course is wrong, it's way too narrow, but essentially that's the general impression. So in fact, Monadic must have good things going for them, otherwise it wouldn't be so successful. And here are three that we can identify. I believe the first is that, well, monadic values are values, and values are good, right? So because once you have values, you can add a rich interface to those values. And in these cases, reactive asynchronous programming, you have lots of operations that need to be supported and that essentially would add to flexibility if you can support them in a pluggable way. So for instance, scheduling tasks, canceling tasks, tracing tasks, that's all quite difficult and complicated, and these modern monadic frameworks, they provide all that. So that's good. Now, when you have such values, then of course you need to compose them, and there really monads shine, because at the bottom of it, the fundamental operation is sequencing of these things. I mean, you also have parallelism, but that's much coarser. So the fine-grained composition is sequencing, and of course, monads are the right way to express sequencing. But the monadic approach also has problems, and I believe the first quite obvious problem is that monadic code does look like nothing like direct style code. So it's essentially a bunch of binds of flat maps, and there can be syntactic sugar like do notation in Haskell or for expressions in Scala, but it doesn't look anything like direct style. Direct style is much more flexible. You can essentially intersperse println where you want. You can use recursion unrestrictedly, and so on. And furthermore, if you want to switch from one to the other, it becomes very awkward. So let's say you have a nice monadic program. You wrote all your for expressions and so on, and then you want to put a println somewhere in the middle of a function, then that wouldn't work, because the println essentially, no, sorry, it should be the other way around. You have a nice direct style program, everything is pure, everything is functional, is referentially transparent, and now you want to introduce an effect like a println. Well, you have to switch to monadic code if monads is what you have to express effects. So you have to rewrite your whole program into do expressions or for expressions and so on. The other big problem with monads is something that I believe Oleg was one of the first to notice, that that composing several monads is also very awkward. Monads don't really compose very well, and what people usually did was use monad transformers, and that's something that can be quite cumbersome as it scales. So that's why people have looked recently for essentially different ways to do things. There was a year in the Scala community of free monads, and then there was a year of finally tagless. But all these things are a bit heavyweight and difficult to onboard new people, clunky, you could say. So what happens now is that real systems often actually revert to saying, well, let's not compose monads at all. Let's invent a super monad that has everything that we can conceive in it. So it has some environment component, some error component, some result component, and let's just work with that, because it's so much simpler to work in a single monad than with several of them. But of course, that sort of this one-size-fits-all approach is not good for everyone, and definitely lacks modularity. You can't pick and choose your effects anymore. So another new thing that, well, not so new, but a thing that recently gained a lot in popularity was to hide the difficult monadic code with async, something like async. So here you see an example. So we have an async block, and async blocks gives you a future, so something that happens in the future. And inside the async block, you can have other async blocks, and you also can have awaits. And essentially an await waits for a future, and then continues with essentially the future result. So inside an async, you use direct style for everything, but outside, essentially, you get the future. So that avoids you writing all these monadic compositions. That was available, I believe, first in C#. It was itself influenced by workflow expressions of F#. It's also available in Scala 2, in TypeScript, Python, Rust, and many, many other languages. In Scala 2.13, so that's the last version of the Scala 2 branch, we're now in the Scala 3 branch, that allowed async to be compiled, also to be coupled with user-defined monads. So it wasn't just tied to a single thing like a future or a task, but you could essentially determine what it was defined with. So that's actually nice progress, but it will turn out we can do much better than that. So what async essentially does is a syntactic sugar on top of monadic code. That's not always what it is implemented like. So it's often implemented with a state machine or something like that. But at the outside of async blocks, you have a monadic interface, a future or a task or something like that. So you could see these state machine implementations as essentially just a local optimization for a bunch of flat maps. So async is nice because you can use direct style, like I said. So at the top of the slide, you see a typical usage. You have async, and then you have two awaits, x and y, which let's say they both give you an int, and you sum them up. But it doesn't really get to more interesting use cases. So the next thing already doesn't work. So let's say, well, let's not just sum two numbers. Let's sum all the numbers in a list and each number in a list is a future, so we have to wait for it. But unfortunately, we can't write xs.map_await.sum. The problem is that async is a syntactic transformation. So basically, everything that it touches, the compiler has to see. And map is a function, a higher-order function that comes from the standard library, so the compiler can't touch it. And therefore, essentially, the connection breaks. You can't thread async code through code that isn't prepared for it. And that leads to essentially a split in the ecosystem, that you have essentially code that is async and code that is direct. And you have to pick which is which, and they can't essentially take on any other role. So there's a famous essay by Bob Nystrom written titled "What Color Is Your Function?" that essentially treats that in a humorous way. It's a very nice essay to read, but it shows a real problem that essentially async invariably leads to this ecosystem split. So if we change the setting a bit and say, well, what these things all did was basically map things back into monads. So, but let's say, well, monads basically pretend that you run on Lambda calculus, you run on a purely functional thing, and monads add selectively new functionality, both in the types and in the operational runtime. But computers are not like that. Computers have much richer runtimes. So they have exceptions, they have side effects, and more they also have continuations or coroutines or something like that. I mean, computers can, of course, do all that, they're Turing machines, but I mean actual runtimes on which we're interested to execute our programs. So these things can replace monads if we choose so. We could use exceptions instead of a monad like try. We could use native side effects instead of monads like st for local effects or io for global effects. And we could use continuations or coroutines instead of all these reactive abstractions like future, task, or control. Then we could, in that case, we could avoid monads. But we haven't really gained that much because essentially we lost typing. We lost the typing aspects. We can use all these things in an untyped language or in a typed language that just gives us access to these things, but they don't show up in the types. And that's a problem because we typically want to know about these things. You want to know what exceptions your program throws, because that should be part of the contract. You want to know whether your function is pure, referentially transparent or not. And you also, in particular, you want to know whether something can block or not, might wait indefinitely or things like that. So all these things are important things to reflect in the type system. But on the other hand, once we decouple the operational semantics from monads, we can also investigate other ways to express the typing. And there are several interesting ones. And one particular interesting way to do the typing of these things is via capabilities, to use capabilities for tracking effects. So instead of saying, I have an effect like an exception, I can throw an exception, I say, well, this code needs a capability to throw an exception. We comes down more or less to the same thing, but capabilities have several aspects that make them quite interesting here. So what about monads then? In the end, we want something like async await, so that can couple with monads, that can glue monads together, but without the restriction. So we want to write it and thread it through map and things like that, and not tied to a specific monad. So we want direct style to interrupt with different monads at the same time. And in fact, that has been done in the Semantics a long time ago by Wilinski in his paper Representing Monads, 1994. So he showed that we can implement arbitrary control effects in the underlying language if the underlying language has support for composable continuations. The implementation is done with two primitives, reflect and reify. So reflect takes a monadic abstraction, that's the T of A and the type rule, and essentially gets you out of the monad, which is something monads don't provide natively. So it lets you map a M of A or T of A to an A. And reify goes the other way. So it takes a simple computation of type A and turns it into a monadic computation of type T and A. If we go back to the await async framework, then reify is async, so it's on the outside, and asynchronous computation and reflect is on the inside. It's the awaits. So that also means that for safety, we need to ensure that every await or reflect is inside an async reify. We can't have a reflect that's not encapsulated by a reify dynamically. And to ensure that, we can use a capability. So the capability would be provided by the reify, so it would be created by the reify or async on the outside, and it would be passed down to all the locations where we want to await or reflect. And it would also essentially provide the means for essentially then do the control operation that does the await or the reflect. Okay, so that's the principle. How do we represent that in Scala? So we have developed a little library to implement Wilinski's ideas and to connect with existing monad stacks of existing libraries in Scala. It's all centered around a trait that represents monads called Monadic. So Monadic takes a type constructor, that's the M here, and it has the two obvious operations, pure and bind, with the obvious signatures that you know. That's actually the sort of the pure view. In practice, what we used was something slightly different. Instead of bind, we used an operation called sequence, which essentially has trampolining built in. That's because Scala runs on the JVM, which doesn't have tail call elimination. So we have to be careful that we don't overflow the stack, and sequence does that. Sequence is like bind, but the function, it doesn't just return a monadic result with the new result type R, but it can opt to give you back essentially a signal that it wants to be called again after the stack is unwound. So that's the trampoline functionality. But it's essentially all encapsulated in this framework, so it's not really, user code doesn't really have to deal with it. Okay, so once we have that, we can now define reify and reflect. So reify takes an operation, that's this prog here thing, and runs that. That operation is a direct style operation, and it runs that. And of course, the operation needs to have access to a reflect operation. That's the trait that you see at the top here. So reflect says reflecting on a monad means that I can get out of the monad. I essentially put in a monad value, like a future, and I get back the value of the future without blocking. That's because we run in an async context, so everything is essentially on demand asynchronous. So just for those of you who don't know Scala well, this colon monadic here, that's basically a type class. So it plays the same role. It says the type constructor M must have the monadic type class. We call it a context bound, and it's a short form to express an implicit parameter. So we don't have native type classes. we have these implicit parameters that get passed with these using clauses. So what this says is we have verify, it takes a constructor M, and there must be a monadic instance for M that's essentially the compiler can synthesize for us. So that's the using clause. The other piece of syntax here is this question mark arrow thing. That denotes a context function. So we have established that essentially the code inside a verify must somehow know how it can reflect. So that gets passed in as a parameter. But for convenience, we don't want to thread that everywhere through the code. That would be way too burdensome. So we use an implicit parameter instead. And so what this question mark arrow says, it's a function. So it's a function from reflect to A, but it's a function that gets applied implicitly. So it's a function with an implicit parameter, and the parameter gets resolved automatically every time the function is referenced. So that way we avoid the burdensome threading of things through the direct style code. If you want to find out more about that, so there's a paper in Popper 2018 that essentially develops a theory and use cases for these sort of abstractions. So here's a simple use case for our reflection. We have an abort method that essentially takes a reflect of option. So what we want to do is we want to essentially reflect on the option monad, and if you do that direct style, you get essentially something that of computations that can abort. So here's the abort operation. It takes a reflect of option, and it just essentially finishes the computation with none as the value. And then we have a save div operation. So save div says if the divisor is 0, then we abort, and otherwise we provide the division. And then we put the whole thing in a verify that says, well, our monad is option, our final result is int, and let's do 2 safe divisions with 4/0 and 5/0. So what this would do is the first time it would hit a safe div, it would return none. And if the divisor wouldn't be 0 but something else, then it would give you back an optional value, a sum with the actual result. We can also abstract this out a bit. Reflect and verify always makes my head spin a little bit. So we can put that under nice abstraction. So we can define a type optionally A, which is essentially the result A as a result of the implicit function that takes a reflect of option. So we take a reflect of option implicitly and return an A. And then we have a constructor for that, also written optionally lowercase, that says, well, we have an optionally computation and we turn it into an option of A. And that's just a verify. Once we have that, we can write the example nicer. We can write save div. We can say that's optionally int. And then we run the whole thing in an optionally context. You could say, well, how is that different from option? How's optionally different from option? Well, it's different because what you see here, it's direct style. So we just essentially can have the addition of 2 safe divs. We use it directly. We don't try to pull out things from an option with a pattern match or a get or whatnot. So it's direct style. You just write things as on the happy path. That means you get a result, and if something goes wrong, then you essentially abort through a control operation. So that you could have expressed with async, or an option-like version of async, of course. But here's a more interesting use case. You can also say optionally list of 210 map save div of 22 with essentially the values in the list. So you go through the list, and each list value becomes a divisor of 22, and then that's the list that you return. And that, as you've seen, you couldn't do with essentially a purely syntactic construction like async, because it doesn't take, essentially map wouldn't know about it. But if you have underlying control that is universal, then of course you can. Okay, so what we can also do is we can combine effects, and that's where it gets even more interesting. So we can say, okay, now that we have optionally can verify an option, we can also reflect on futures. Reflecting on futures is essentially just direct style asynchronous programming. So here you see at the bottom, you see a combination of the two. The inner code says, well, we reify in future. That means that lets us read a text file, and reading in this framework is a future. So at some point in the future, we get the file back. Then direct style, we take its size, and also direct style, we add save div 50 to it. So that's now two monads that we have composed. And if the future comes back, we get its size and we do save div 50, then we will exit directly out of the option reify and essentially skip the future reify. So that shows that we can essentially have these layered monads in this style, which if you use them like monad transformer are a big headache, because that means that it's much harder to compose than in this way. So the implementation we have is in Scala on top of Loom. Loom is a native coroutine implementation, currently in an early access JDK. It's hopefully scheduled in some future version of Java Virtual Machine. We don't know yet which one exactly, but it will hopefully be not too long. It's available from the GitHub address that you see here. It showcases integration with several popular monad and async frameworks, including Cats-Effect, Scala Z, Zario, and Scala Concurrent Future. So you see that there are quite a lot of them out there, but the nice part of the generality of monadic reflection is that it works in all of them. Essentially, the only thing an implementation has to do is implement the monadic interface. So in summary, I think the take back is once we have a runtime that supports coroutines or continuations, we can mix monadic and direct style computations with reflect and reify. And that, in a sense, gives us the best of both worlds. It gives us the composability of first-class monadic values, the good parts of monads, but also the composability of different effects. That's where monads had problems. And what's more is we can integrate nicely existing, widely used monadic libraries and thereby provide a smooth migration path forward, which is interesting, important, because, I mean, people have invested a lot in these monadic libraries, and there are many, many millions of lines of codes written in them. So to put a perspective on that, quite recently, Brian Gutz gave an interview. Brian Gutz is the Java lead at Oracle. He said, I think Project Loom is going to kill reactive programming. I believe it's reactive programming. He means these ways to represent things with monads. He has a point in that he says, well, previously, without coroutines and continuations, the only way to get reasonable reactivity, that means essentially that we can have many, many concurrent operations, most of them are waiting for some events, was with these monadic frameworks. And now with Loom, with native coroutines or fibers, that's no longer necessary. So will it kill reactive programming? I don't know. I think probably not immediately, certainly, because what is proposed by Loom and fibers is, of course, a very imperative coroutine implementation. So that solves none of the problems of composability and so on. But in any case, whatever happens, monadic reflection is a good lifeboat for the monad things, because, as we have shown, they let you use the monadic code inside a direct style framework, and it maps to Loom and coroutines. I should say there's one caveat that I have glossed over. Well, there are two. One is Loom only implements specific one-shot coroutines currently, so that means they only work for monads that work with those sort of control operations. So it doesn't work for any monad, but it works for enough monads that I believe are currently of big interest. The other caveat is that once you work with capabilities, you have the problem that like any values, capabilities can be captured in closures. And that can lead to problems if capabilities have limited lifetime, because you want to have a limited lifetime of a capability, then you pass it in the closure, and the closure might survive the lifetime of the capability. So an example is here that you see here. We have a reify option int, and instead of doing two save divs additions, we put them under a lambda. And now if you want to try to use that like this, that we say, okay, give me back what you just verified. That will be sum of some operation, a function. Let's apply the function. and if not, let's return 0, then the fiber handling the reify will probably have terminated before the safe div call aborts, and that would be a runtime error. So that's essentially an inherent problem with current capabilities. And what we're doing also is we're working on type systems that can track ephemeral capabilities. So those are capabilities that have bounded lifetimes. And such a type system could ensure the safety of monadic reflection by preventing that the reflect capability can escape from the scope of a reify. So you see here at the bottom of the slide a link to a paper that we have on arXiv on that. That's it for the talk. Thanks for listening so far, and happy to take questions.
That's great, thanks. So we have a question on the Q&A. Is the layering order of the effects baked into the type of the computation? The example, the type of the term read file size plus safe div 50 has to match the order that option and future are peeled off.
No, in fact, the option yeah, so, well, sure, the layering order is baked into the type of the computation. Yes, absolutely. So the type as seen from the outside is exactly that. But of course, you can simply swap the two things, and if you adjust the types, so you can do it either way. No, wait, sorry. No, the type of the term read file size and plus safety 50 is just int. There's no monad in that type. The type, essentially, the monadic types come when you look at the whole computation from the outside. And in this case, because the outside reflect was on an option and the inside reflect was on a future, you will get an option of futures. If you swap them, you would get a future of options. So the outside, the layers of the reflect determine the type as seen by the outside, but not the inside. The inside, in the inside, everything is direct style, so it has the simple types.
So I actually have a follow-up for that. So one issue with monads, as you said, is the modularity, because the type really bakes into the type everything that has to be combined. And one way people get around this by saying language like Haskell is you quantify over all possible monads. You can also say, if you give me a monad and that monad has something, then I can do this. And here you're proposing futures as a little bit of an alternative, but it doesn't seem very flexible, or rather it's ultimately flexible, right? You kind of throw in the whole future in, and that's it. You don't have any tighter control over what can go in the environment and what can. Do you find that's a problem in practice, or how does that pan out in practice from your experience? Would you prefer tighter control?
Yeah. Well, the one system that quantifies all possible monads that I know best is finary tagless. So finary tagless can do that, but it's still it's essentially, I see it as a DSL that's very stylized, very general, but it sort of also requires global buy-in. So everybody has to keep to the same style. And in practice, that's hard to achieve. You have a lot of heterogeneous systems. You can sometimes do it, but so there's currently a big debate ranging over finary tagless versus a single supermonad, and it seems the supermonad people have essentially very strong arguments why this monad parameterization approach is just too complicated. Since I don't write a lot of this reactive code myself, I'm a sort of an interested bystander. So I can't really be the arbiter which one is better. But it seems that it's not a done deal.
Just to add one thing. So if you have code that doesn't use one particular monad in this monadic reflection setup, you don't need to do anything. You can just write your direct style code. So you don't need to quantify over all possible monads. It just works. You just write your direct style code without mentioning any monad, right?
When you mention the future. Oh, okay.
Yes.
I mean, I'm staying away time from your talk. So
no, it's fine. My talk is shorter.
Okay. Do you want to go with the video, by the way?
Oh yeah, if that works.
That should work. Okay. So Martin, thank you very much. There's going to be ample social time to follow up on this.
I'm sharing my screen.
So let's thank Martin again, and let's see if this works. Now I need to find Jonathan's video. Sorry, this is the first time. There you go. Play on stage. Oh, and looks like we're back, but
okay. Well, Ohad, so we're starting. Okay, let's start the second session. Before we start, however, I have one announcement or encouragement to presenters. You can still log into the web page, ICFP web page for the HOPE workshop and set up accompanying materials to your talk. For example, you can link to your paper, to your slides, or to anything else that you think might be relevant to your talk. So please, there is still a time, and please do that. I hope that you consider it. Okay, so the first talk of the second session is by Willem Heiltheus on functional machine calculus. So Willem, please.
Thank you very much. Pleasure to be here, so to say. So this is about a new model of combining higher order computation, Lambda calculus, with effects. So a quick overview of the history. Since the 60s, we know how to do call by value with, so eager evaluation plus some constructions to delay evaluation. But that's not all we want. We've seen how to do it in continuations, call by name with monads. There's this line of work, kappa calculus, that might be familiar. Premonoidal categories may be a little more familiar. Haskell arrows, I suspect, is familiar to most people. Then we have call by push value and friends, and recently effect handlers. So there's a quick overview of what paradigms we have floating around, and I don't think this is exhaustive at all, for sequential higher order computation with effects. And the functional machine calculus fits into this series, as it were. I would put it above effect handlers. I put it in here. What are the requirements of a model of computation of this kind? Well, first it needs to express multiple strategies, right? You want to have lazy and eager evaluation, and you want to have that in the syntax so that the programmer can decide when the effects are called. And sort of less strictly, but in practice very relevant, is that you would want an intuitive notion of sequentiality, because effects are sequential. At least we are talking about sequential computation. Of course, there's also a separate branch of concurrency, but it's not about that. So we want sequentiality. So this work starts by observing, well, bit reduction is not sequential, right? And that's the reason why we have all these different paradigms. But call by name evaluation with a simple stack machine is sequential. So the Lambda terms do have a notion of sequentiality in them, and that is the spine. So an application, mn, pushes the argument and then continues as m. So this is an operation, and the sequentiality is to do some is continue on the m, so that on the spine. And an abstraction pops a value n and continues as m with n substituted for x. So I'll write this as prefix. So the spine of a term, which is here continues as m, and here as well continues as m, is a sequence of machine instructions for a simple call by name stack machine. So the first thing, so the functional machine calculus will feature two generalizations of Lambda calculus, and the first thing I need to do is to adapt the notation so that I can add these. This notation emphasizes the stack operations. So it's the same thing, but written differently. It's a push operation pushing n, and a pop operation popping as x. That's it. Just a change of notation to make everything, to make the machine perspective more intuitive. So then we have stacks, which I put the elements, the head, to the right, and that's because then a sequence of these push actions will produce the stack in the same order. And states are a stack and a term. And then these are the transitions. So this is just a formalization of the intuitive stack machine that I just mentioned. So this is a push, and this is a pop and substitute. And terms look slightly differently. So for instance, the S combinator will look like this, and this is 2 applied to 0, it will look like this. So look like the argument goes to the left. So it takes some getting used to. But the payoff is that we get a notion of sequentiality in our terms. And we can make an observation here. So the spine of a Lambda term, right, becomes, that's simply the top level sequence here. And so this is another Lambda term. So this is also a separate spine. A spine is a sequence of actions that ends in a variable. A variable ends the spine, and it must represent all of the remaining computation. When you look at this as an instruction sequence for this simple stack machine, that is a really weird restriction. For the machine, it would be absolutely fine to have variables in the middle of the spine. And it would just, you can put a sequence of instructions, you can substitute a sequence of instructions and continue after doing that. So this is what we do. The first change to Lambda calculus I've called this the sequential lambda calculus, is this. The variable, the usual variable construct, is split into a null term, an empty. This represents the empty sequence of instructions. And the variable now becomes a prefix. And just like the push and pop actions. So now we have, now we can build any sequence of push actions, pop actions, and variables into a term. So here are some examples. So this pops something as x and then pushes it twice. This pops two things and does nothing. And well, let's first change the notation a little because those dot stars are getting in the way of reading what it actually does. So I'll omit those, the trailing dot stars. And then you can see, well, this is it. Pops x and pushes it twice. This pops two things, and this is the identity. It pops something and pushes it back. So the identity for non-empty stacks, that is pushed onto the stack. It's read and bound and executed 3 times. So the thing to note here is that these are not lambda terms. These are this makes no sense at all as a normal lambda term, but as a sequence of machine instructions, it is absolutely fine. There's no problem with this at all. And what do we get? We get some nice things. So here is notion of composition, right? Because we are talking about sequences of effects with variables anywhere. We can now compose them. So semicolon for composition, and this is the definition. And note that we have to do capture avoidance, right? If we compose something, then x here binds in n. And if you put all those actions in sequence, it might bind in m as well. So we need to do capture avoidance, and that's this. Substitution is as expected, and the special case, the new variable case, substitutes for x and substitutes in m, and the prefixing becomes a composition, of course, as expected. And then beta reduction is as normal. So features of this design. So variables now, so the main change is that variables are something different. Variables no longer represent lambda terms, they represent sequences of instructions. In a way, you can see this as variables representing computations and not values, but that's both helpful and could also be confusing. We get the notion of composition and a unit and empty sequence, and it's conservative over lambda calculus if we restrict ourselves to those sequences where the variable and the unit always occur together. We just have lambda calculus again. But this is the really nice thing. With this simple change, you can encode call by value lambda calculus, the monad approach, the computational meta language, call by push value, and arrows. So it's a very simple change, but it just these other paradigms in an easy way. And I'll show 2 of these. So here is how we would encode call by value lambda calculus. So this is the call by value lambda calculus. Values are variables and abstractions. And then a reduction requires that the argument is a value. Encoding is as follows. A variable becomes a push action on a variable. And an abstraction adds a push action as well. So what's happening here is that instead of return, so to return a value, right? A value is something that is returned by the computation, and to return something, we push it on the stack. Just quite a normal thing to do. And note how this is not expressible in normal lambda calculus. And if you want to do these kind of things. Normally, you'd have continuations. You need a continuation to do that. But here, we can simply have a term that consists of a push action and nothing else, and the same here. And then for application, so this one evaluates the argument first here, and you can swap these around. You can do an encode function first evaluation by turning these around and fiddling a bit with it. But this is the easy one. So argument first, function second, and note that if this is a function, then it will evaluate to a push action. So evaluating this term will leave the function m pushed on the stack. So then we need to execute it. So we pop it and we run it. And that's what we see in reduction. So here is the reduction step again. And if we have, if this value translates to this push action, then what happens is, well, we push n, we push the function. Oh, this should have a, yeah, that's all right. And here is the evaluation. So the reduction here is, this is the redx, which just substitutes m for y. And that exposes this redx, which becomes a substitution. And that all works out. We also encode monads. So in the meta language, it's written like this. In Haskell, it's written like this. So there's two operations. The return operation and the bind operation. Here it's used as a let, and in Haskell you can do it without having an explicit variable. But anyway, that's fine because we can encode this easily as well. It turns out this is just its composition. Oh, I should say this is really a semicolon, but I'm lazy and I'm just using dots everywhere. So I'm using dots. I'm overloading dot for prefixing and composition. So I hope that doesn't throw anyone off. So the idea is, as in call by value, the return of a monad is it's pushing its return value onto the stack. And the let is a construct, or the bind is a construct that evaluates this first and then continues with that, and it pops the result of that computation. And it's immediately, it's very straightforward from the translation, but the reduction works. So return this and then bind it in M. This would evaluate to that. And that's also what happens here. It's very straightforward. All right, so now, we have our encoding of strategies. What do we do to add the effects? So here's another observation. Basic effects, like input, output, and state, can be encoded with pop and push actions. Input is, reading from input is a pop. Writing to output is a push. And states can be modeled as stacks of depth 1, where update is first pop, discarding the value, and then pushing the new value. And lookup is popping and binding and pushing the same value, the pop value, back to restore the state. But what's different from normal Lambda calculus is that every effect uses a different stack or string. So that is the second change. We parameterize our abstraction and application and abstraction in a set of locations. And each location represents an effect. We have a main location, central location, which is sort of omitted from the notation for for the general application and abstraction, and then we can encode these various effects by adding more locations. So overall, we have a Lambda calculus with two generalizations. First, sequencing, which we've seen before, split the variable into a unit and a variable with a continuation here. And the second is to parameterize the abstraction and application as push and pop actions in a set of locations here. So here's some examples. So this could be a random generator, and this could be output, and this function would read from random and output that value. And this would do that. It would store that function on the stack, pop it as f, and execute it 3 times. So this would take 3 random values and output them. And here is something weird. What does it do? It reads a function. It reads from a memory cell C. It puts the value of it found at C onto the main stack, applies f to it, reads the result of f, and pushes to C. So this applies, it takes a function f and applies it to the value stored at a memory cell C. The stack machine for this is as expected. We have a memory, which is a family of stacks. So one stack or stream for every location. And I'm writing them with a semicolon, and then I'm immediately breaking that notation for convenience. I'm murdering it here. So states are pairs of a memory and a term, and the transitions are as before, except they operate on the stack indicated by the location, and that's it. You push to that stack and you pop from that stack, and everything else is as before. And then we can check that the encoding of state works as the intuition would suggest. So we can model a memory cell by a location C. We don't have to restrict it to have at most depth 1 or exactly depth 1, because the operations will make sure of that. So an update, which I've written with the continuation, with the remaining as a prefix instead of a separate thing, but it could just be a separate operation, is pop and discard. So this is a non-binding variable. Push n and continue as n. Lookup is pop from C, restore that value to C, and execute it. And the machine, the stack machine, shows you that operates as expected. Right? The transitions are what's needed. So here's an example. This is without sequencing. So this is an example that's within the normal range of the Lambda calculus with effects. The encoding here, so the example, it has a memory cell A, and it sets it to 2, and then it has a function and an argument. The argument will set A to 3 and return 0, and the function will throw away the argument and read A. So this is to illustrate the divergence between call by name and call by value. The call by name evaluation would throw away this update, and so it would read 2 here, and the call by value reading would execute it, and so it would read 3. And this is the what happens is, this is the encoding. The update comes here. The argument to the function is a push action here. Here's the abstraction, and here's the read A. And to produce that in the machine, it's very straightforward series of steps. We have to initialize the stack for A with a dummy term, so that we can pop here, so that we can even start. But if we do that, then we update. So the first thing is to update A with 2. Then we have the redx, which is, so this is pushed onto the main stack, the Lambda stack, and then discarded in this step. And finally, this read operation, it reads from 2 and restores it. Beta reduction in this calculus needs to account for the multiple stacks for the enlarged memory, and that means we have to allow other abstractions and applications in between a redx. So this could be actions that operate on other stacks, not on A, but they can't be variables or they can't be actions on A. And then we have a redx that goes like that. And here's a theorem. This reduction is confluent. And is that surprising? Do we have a response? Is anyone surprised by that? Let's see if people are still paying attention. My referees surely were.
Is this non-deterministic? Sorry, I may have missed.
Sorry?
Is the reduction non-deterministic at all?
It's just beta reduction. It's non-deterministic. It's it happens anywhere. It's a rewrite relation. So you are surprised?
Slightly.
So this is why. This is why it can be confluent. So beta reduction does not evaluate effects according to their operational semantics. So we have, on the one hand, we have this stack machine, right, which operates beta reduction as the Gravine machine, and it evaluates effects by their operational semantics. And on the other hand, we have beta reduction, which is sort of an optimization when you look at the machine. And if you apply beta reduction to the encoding of effects, this is not the operational reading. You get the algebraic reading. So this is what happens. If you encode 2 successive state updates, they become 2 sequences of pop and push actions, and they interact. So the push action of the first and the pop action of the second form a redx that reduces, and that reduces according to the algebraic laws for effects. And similarly here, the state update followed by a read action is the same, is algebraically equivalent to the same update followed by executing that the updated value. And the same thing happens here. This is a sequence of pop and push actions, and at the boundary they interact, they form a redx, and they give you the expected algebraic operation, the result of that algebraic equation. So here's an example, the same example. For instance, in this term, we can see that this push action is adjacent to that pop action. So there's actions on other stacks on the main stack in between, but that doesn't matter, right? We know that these don't affect this redx. So this is a redx, and we can update that. And then we can do that one as well. And we see that the term reduces to the to this action, to this term, update the state to 2 and return 2. So quickly, the other effects. So input and output, reading is a pop action and writing is a push action. Nothing spectacular about that. To get going with this stack machine, we need to have a stream of inputs, and for beta reduction, we need a contextual and applicative context. And then we can do probabilistic choice and non-determinism as in the same way, by having a random generator or non-deterministic generator represented as a stream of inputs. Okay, I have 4 minutes, I think. I'm not going to make it to types, but I'll do a bit of programming if you'll allow me. So, how would you program with this calculus? So we've seen with monads and with call by value that the return values are encoded by pushing them onto the stack. And this is the natural way of programming in this way. So the Lambda calculus leaves the return value as an unevaluated remainder of the term. But that doesn't work well in this setting, because if you compose, right, so if you have that value and then you want to compose that with the remaining computation, then you can't pick it up. It's just there. It's blocked. Reduction is blocked. The machine is blocked. It's done. So instead, what you would do when programming this is you would do as in call by value and as in the monadic encoding. You put your return values on the stack, and then you can compose with a function that pops it again. So this is what we expect. A term M should be considered as taking an input stack S, and then producing an output stack T, or an input memory S and input memory T. I'm dropping the locations when it's convenient, because they're straightforward and just clutter things. So then we have the empty term as identity, and we have a notion of composition. Composition is composition. So if we have a term N that takes R to S, and we have M that takes S to T, then composition, dot or semicolon, will take R to T in the machine. That's just what happens. Okay, let's add some primitives. They will work just as expected. A plus will take the top 2 items and add them and return a skip. A conditional will read 3 values, and the last one is the Boolean that determines which it takes. Ooh, that's one of these should be an M. I clearly couldn't decide which. And we can do inequality in the same way. And then you get, for arithmetic and Booleans, you get a simple standard stack calculus, which where these are pop and push actions, as you would implement a calculator. Then for effects, we wouldn't do the encoding as before, but we would use a separate get and set actions that operate on the stack. So a get would read from memory, restore the memory, and put the red value on the main stack for use by the next function. So get C, it's a read operation read from memory, and it puts the value on the stack instead of evaluating it as before. And set C is the same as before, except it reads its argument from the stack. A print is convenient to have. It reads from the main stack and pushes to output. Read takes input and puts it on the main stack, and random similarly. And definitions or let bindings can be encoded as radixes as normal. And then we can write something intelligible. So we define f as the function that takes a random number, sets the location C to that value, and then reads from C again. So that's the definition of f. Then that's executed twice. The output of that, which is what it got from C, is added, and that is printed. And I will go through this quickly and here. This works. So here's the beta reduction. It reduces inside arguments, right? So it reduces anywhere to basically to optimize the function f. And here we've optimized f, and we can duplicate it here, and then it interacts with itself. Here we're out of redexes, we're in normal form. We take the machine, and it's a simple sequence of stack actions. So we have a random generator which presents two numbers, and we have a location C which is initialized with the null term, and we read from random. We pop the C location. So the random we read was 7. We put 7 on the main stack, well, etc., etc. And the main thing is it ends up with having put 6. So the last read value in C, right? So C is updated with the last read random value for every execution of f. And we've added the outputs, so to 13, and put it to output. So I think I'm out of time. I would love to do the rest, but some other time maybe.
Okay. Do you have a conclusion slide?
No, the conclusion slide says thank you. So I'll conclude with that.
Okay. Okay. So, well, thank you. So it's a good conclusion. So we really don't have time, and so probably it's better to have a discussion in the lunch or in the chat. Well, let's thank the speaker again. And now the next speaker is Timothy Tomandl and Dominic Orchard. Well, Timothy would be the speaker, and joint work with Dominic Orchard.
Hello?
Timothy?
Hello, can you hear me?
Okay, yes.
Okay.
The last talk of the session by Ricardo Trail. There is a video, right? So.
Yeah. Can I start it? Is that okay?
Yes.
Okay.
Ricardo, you can speak, right? And we can hear you.
Yes, I can. I think you can hear me.
And
yep, I can hear you.
The video to be played, right? Should we start the video?
Yes, thanks.
Okay. Ohad, could you please?
I'm going to present a joint work with Claudia Fagian and Giulio Guerrieri. It will be about the computational calculus, specifically in how to bridge reduction and evaluation. The computational lambda calculus was introduced by Moggi in late 80s as a meta-language to describe non-functional computational effects in programming languages. Since then, computational lambda calculi have been developed as foundations of programming languages, formalizing both functional and effectful features in a still active line of research. To model effectful features at a semantic level, Moggi used the categorical notion of monad. At a syntactic level, instead, the use of the monadic approach is internalized by considering the 3 monad laws as 3 conversion rules that are added to the user reduction rules. Therefore, computational calculi can be seen as call-by-value settings plus the 3 monadic laws. We study the rewriting theory of computational lambda calculus. Our interest is driven by the fact that rewriting theory provides a sound framework for reasoning about program transformations, such as compiler optimization and parallel implementations. Many interesting and fundamental properties are given by such an investigation. Think, for example, confluence, leading to the uniqueness of normal forms. Now, let's synthesize the objective of the present work. Historically, Moji considered a reduction relation that is full, while in the actual implementation and in literature of calculi with effects, we have strategies that do not allow reduction under any binder. In the end of this talk, we will state our bridge between these two notions, reduction and evaluation. Specifically, our investigation is about the rewriting theory of the computational lambda calculus given by Sabri and Waldler. That is a neat, simpler reformulation of Moji's original one. There is a strong relation between these two calculi. But before embarking on details of this calculus, let's stress how computational calculi can be seen as a call-by-value lambda calculus plus 3 additional rules given by orienting the monadic laws. Lambda ML star is an untyped calculus that was introduced by Sabri and Waldler in 1996. It has a two-sorted syntax that separates values and computation. This separation is nowadays quite common in the literature of computational calculi. Values are, as usual, variables and abstractions. Computations are either coercion of values into computations, corresponding to the return operator in Haskell, or let expressions that are explicit substitutions capturing monadic binding, or application, but please notice that they are just of values to values. As I said before, it's possible to consider ordinary reduction rules as beta and eta, which we do not consider actually, and in addition the tree-oriented monadic laws. The first of them is the beta reduction at the level of let constructor, also called the left unit. The second rule can take place when a term is in a trivial let expression, and sometimes it is called the right unit or identity law. The last rule, the associativity rule, takes place when there are two nested let expressions and disgregates them. Both Moji and Sabri Waldler in their investigations considered a full reduction. That is, the reduction rules are closed under arbitrary context. Such a reduction is surely confluent, but I won't give a detailed definition of full reduction, but let's see how it works in the next frame. Given a silly term like this one in the middle of the page, let x be the self-application of the identity function in the identity applied to x. Full reduction allows to reduce everywhere in this term, such as the inner term, the blue one, or we can also reduce the orange part, that is the subterm bounded by the let. However, standard practice do not consider to reduce the orange part as well. In fact, just the inner subterm is reduced until it is possible to perform a let beta reduction. Let's define better this kind of evaluation, since differently to the full reduction, it turns out to have serious bad rewriting properties. We define evaluation as the closure of the rules under weak contexts. That means that no reduction is allowed under any binder, let expressions or abstractions. Weak contexts are the empty context plus what is possible to construct inside a let operator. Informally, the operational understanding of weak reduction is that evaluating let x be m in n amounts to first evaluate m until it returns a value, then this value is passed to n by substituting it in each occurrence of x in n, thanks to the rule of let beta. In literature, it is also standard to consider just weak contexts and beta and let beta reductions. It is worth to clarify now that while in literature on computational lambda calculi often adopts weak reduction, the rule of associativity and identity are usually dealt with as unoriented identities. The only oriented rules are beta and let beta. Despite the prominent role that weak reduction has in literature of calculi with effects, its reduction properties are somehow surprising for us. While for reduction is confluent, the closure of the rules under weak contexts turns out to be non-deterministic, non-confluent, and its normal forms are not unique. Let's see a bunch of counterexamples to confluence. Please note that such issues will only come from the monadic rules of identity and associativity, not from beta and let beta. Let's consider the following term. Let y be let x be zeta zeta in m in returned y, while m is just a normal form. Here we can perform two weak reductions, both in the empty context. The first one can be an identity reduction. In fact, the inner term is inside a very trivial let expression, just reducing our initial term to the inner term. Let's consider also in the empty context this term, and notice that we have two nested let expressions. So we can disaggregate them by means of the associativity rule, obtaining this second term. Notice that both the obtained terms are weak normal, but m first and second are different. This is clearly a counterexample to confluence. But let's give another counterexample, this one just considering the associativity rule. Consider the following term. Let zeta be let x be let y be L in Q in P in R. Well, all the capital letters are normal forms. Take, for example, just zeta applied to zeta. Well, here we have three nested let expressions, and so we can perform associativity rule, but where? Or in the empty context, or in the inner subterm. Let's consider in the empty context first. Well, we can disaggregate the two let expressions, obtaining this term, and then reapply another associativity rule, since we have again two let expressions nested together, obtaining a weak normal form, well, also a normal form, that is m first. If we consider just the inner term, also here we can perform an associativity rule, obtaining this term, and reapply another associativity rule, obtaining m second, that is a weak normal form. So this counterexample is given just applying the associativity rule. Another remarkable aspect making the reduction theory of lambda ML star tricky to study is the lack of factorization, which is the simplest possible form of standardization. In Plotkin's call-by-value lambda calculus, reduction satisfies weak factorization. Any reduction sequence can be reorganized as weak steps followed by not weak steps. Similarly, it can be done in the call-by-name setting and add reduction, for instance. But in lambda ML star and in similar computational lambda calculi, weak factorization does not hold. The problem here is given by the identity rule. The counterexample that I won't give today was given by Vincent van Ostrom. Why interested also in factorization? Well, factorization is the key property to prove that in Plotkin's call-by-value, if a term m reduces in a number of steps to a value, then m only needs a weak beta reduction to reach a value. This provides a bridge between the full reduction and evaluation. And let's call this result as Convergence Theorem. We aim to reach a similar result in lambda ML star. Despite several drawbacks of weak reduction in lambda ML star, we can still prove a convergence result similar to the one by Plotkin. And since those bad rewriting properties we have just seen, it is not trivial at all. Well, we can prove that to reach a value in lambda ML star, weak beta steps and weak late beta steps suffice. Let's see better the meaning of this result. The bridge that the convergence theorem states is that when interested in returning a value, performing the reduction under arbitrary contexts, the largest gray circle in the picture, is the same to perform the reductions just under weak contexts, and better, just using beta and late beta rules. Since factorization does not in lambda ML star, the proof of convergence theorem is not trivial, as I said. I'll give you a sketch of our approach. We translate lambda ML star in another computational calculus recently introduced by Ugo de Ligoro and me, called the computational core. That is somehow simpler and their calculus, but having the same better rewriting properties of lambda ML star and similar computational calculi. But since it is simpler, we can prove the convergence theorem there. By a sophisticated analysis, we can show that the theorem is then preserved by translating lambda ML star in the computational core forth and back. Let's conclude our talk now. Convergence in lambda ML star relates full reduction and evaluation, and provides a theoretical justification to the following facts. Functional programming languages with computational effects use weak reduction as evaluation mechanism. Indeed, weak reduction is enough to return a value. In addition, in computational lambda calculi, when interested in returning a value, the only rules of interest for weak reduction are beta and let beta, which are deterministic and do not have unpleasant rewriting properties, while the rule of identity and associativity can be safely considered as unoriented identities external to the reduction. With that, I conclude my talk. I thank the organizers and the audience.
very interesting talk.
Thanks.
Well, we have a few minutes before the break for the questions. So if there are questions in chat or Q&A, then I'll be happy to read it, or you can raise your hand. Well, in the meanwhile, I have, well, maybe not a question, but remark that you kind of justify that we all suspected that eta rules that always cause the trouble in call by value, right? So, so not, and also that eta let eta rule, it's actually, when you try to prove it in computational lambda calculus, when you add effects, and then it's one of the most difficult to prove. And so it kind of, I'm glad that it's actually, if you just disregard it, it's actually, it's nice because it's very difficult to prove. The left unit law is much easier to prove. It's standard, but the right unit laws or eta rule is very difficult to prove.
Mm-hmm. Yes, it is. We consider it. We don't consider the eta, but yes, it adds other derivative properties to the derivative theory of computational calculi. Yes, I agree. I understand. Yes.
So it's kind of, I'm glad that, it's very difficult to prove and it's not actually necessary. So that maybe we shouldn't spend that much effort with this. Well, Sam, you have questions, right?
Yes. Can you hear me?
Yes, so we can.
Yeah, good. Yeah, thanks for the talk. I guess it's, as Oleg was suggesting, in some ways it's not that surprising that these associativity and eta are causing the problems. And well, as we know, if you just want to reduce to a value, you only need the beta rules. I was wondering whether you've thought about other calculi, like if you take simply type lambda calculus and just add sums, then you have commuting conversions, which are quite similar to the associativity law you have for let there. If you took simply type lambda calculus with sums and commuting conversions, I don't think you have the same kind of problem. But do you?
No, I'm sorry, we don't consider, we already simply typed the lambda calculus, so just untyped at this moment.
Because I guess
this is actually a very good question that you asked. It's well known to be a difficult problem with this, with commuting conversions, and it's for that reason. It is indeed unconfluent, right? If you understand the thing, that causes all the problem because there isn't actually, a kind of obvious normal form, or at least one obvious normal form, right? So that similar situation that you had.
The reason, if you're just trying to get a value out, then you don't really care anyway, and you just do beta rules. But the reason why Pravets introduced commuting conversions in the case of sums was in order to get the subformula, restore the subformula property, even if you don't have the full eta rule. I guess maybe this is my question is, why would you even want to consider this system like lambda ML star where you're actually applying these commuting conversions? The associativity or the eta rule. It seems clear why you want to apply it, like where you're not restricting it to weak context and you're applying it everywhere. That's general kind of reasoning about your programs. But why would we actually want to use this slightly weird ad hoc rewriting system? Do you have a good justification? People have done it, but were they right to do it, or were they making a mistake?
Yes, there is just a theoretical point of view. It is okay, just an interest. Well, the story starts with this computational lambda calculus introduced by me and Ugo De Liguoro, and then we understood that bad rewriting properties could be represented in other computational lambda calculi. Then you understood that lambda ML star can be seen as a kernel of a similar computational lambda calculi that have oriented monadic laws. And since between lambda ML star and Moji's calculus there is a reflection, we said, okay, let's start studying lambda ML star. This is just because it's simpler, but can be seen as a kernel and as expressive as Moji's calculus. Well, you're right when you say there is an interest on the theoretical point of view. On the application is just understanding that the standard practice is okay. But I can say more. For reduction is an interest on its own, just as I said in the first frames, just understanding optimization, or I can perform a better reduction.
But if I'm doing optimization, then I probably want to be able to do that anywhere in my term, not just in these evaluation contexts.
Okay.
Well, that's true, but suppose you're writing evaluator, which is optimized evaluator, right? And you decided to straighten up let's expressions, like kind of, doing a normal form conversion on the fly, right? Which is actually, when you write evaluator in Haskell, actually often that comes out when you have two nested lets, then you kind of straighten them out. So this is actually quite happens in practice when you write evaluator.
Yeah, but my
conclusion...
conclusion...
it's deterministic because in Haskell, the rule has to apply in order, right? So, but then he showed which is actually good that they apply in order because it's actually it isn't.
But you can fix that particular problem by just completing the relation so that you allow the flattening of lets to happen in the tail as well as in the evaluation position.
Well, in the tail, it means it's under the function. Then it's actually in Haskell, it's very difficult to, right? So it's, some of the let associativity is easy to do, but in the tail position, it's not. So it is actually has a, kind of application. One comes to mind, immediately, for example, if you think about Hintz's backtracking transformers, right? So he has this backtracking, it's kind of free like monads, and then he writes evaluator, and an evaluator he immediately say, okay, here are nested lets, so let's straighten it away. It just comes out naturally. So people use that associativity in writing evaluators.
Okay, yeah,
does not occur because it's Haskell and things apply in order, and we never think about what happens if you do it in a different way. Then it works. So, but it turns out it's well, it works because eventually then you get the beta reduction, and then kind of but
thanks anyway.
So it's it happens in real life sometimes. Well, any other questions? Well, it's 3 minutes before the break, and we, previously. Ohad?
Yeah, there's nothing wrong with finishing 3 minutes early and give people some more break if they want.
Yes, I think that, we can move discussion into the lunch, and,
Yeah, so we'll resume in just over half an hour with the third session.
Okay,
and
and
thank
you again for the presentation.
Well, thanks to you, and many hints given. Thanks.
Great. Okay. Take a break.
Can you see my screen?
Okay. Yes, I can.
Great. Thanks, Oleg.
Okay, so you're on.
Right, yeah. So I'm going to talk about a little bit of work I've been thinking about for a while. A calculus I call handler calculus, and this is basically inspired by the observation, kind of not that surprising, that if we're working with algebraic effects and handlers, well, what are computations? They are trees, so you can view them as data types. And typically what we do is we might add our effects or computations to some existing Lambda calculus. But instead of doing that, I wanted to see, well, can I start with a minimal calculus that only has effects, and then I will encode other features, data types, functions, sums, products, etc., on top of my other calculus. So this is my attempt at doing that. And it's a lot of these things I've kind of done before, but this is just sort of bringing them together. So quite a lot of it was inspired by what we did with Frank. So that was with Connor McBride and other people. Programming language for effect handlers. Okay, so I'll just begin with I'm going to kind of skip over these first few slides. Probably this is just an introduction to why we want effects. So, idea being that having pure computation is not enough in practice. We need some sort of interaction, and this picture here is showing the program talking to an operating system that communicates with the environment somehow. We have lots of different forms of effects. Effect handlers are a nice way of generalizing over all of these things that give us a composable, customizable, user-defined interpretation of effects in general. And in particular, they give you direct access to the environment. So very similar to what we get with resumable exceptions or monads or delimited control. Plus, effect handlers are actually seeing quite a lot of impact in industrial practice. So this is a useful thing. And then this picture is kind of depicting this idea of effect handlers as composable user-defined operating systems. So inside our actual program, we might have these little effect handlers, and they provide various interfaces, and you can plug them together. But anyway, this is just some introductory material. Hopefully, most of the audience know about effects and effect handlers. I'm going to also give you one little example. Just to give you some notation. So this is, I mean, in Darnell's previous talk, he was talking about preemptive concurrency, but here's the classic cooperative concurrency example. So let's assume we have an effect signature with a single operation that's called yield. So it takes just a unit and gives you back a unit. And we want to implement some form of lightweight threads. So I might have these two threads here, and this is just to illustrate how the interleaving of these things works. So the first one is going to print out a value, then yield, and print another value, and the second one's the same. And what's nice about effect handlers is we can actually define the cooperative concurrency just directly in our programming language. We don't have to hardwire anything. So here's a canonical example of a cooperative concurrency handler. It takes, so it's actually a function that takes a collection of all of the current resumptions or threads. So if that's empty, then we just return unit. If it's not empty, then we take the first one in the queue and we handle it. And then the structure of a handler has two parts. It has what to do in the case that the computation finishes and we return a value. It's going to return the unit value. Well, we just keep on handling all of the other resumptions. That's straightforward. And then if we come across, this is the important part of effect handlers, where we actually come across an operation, and our only operation is yield. But as well as getting the payload of the operation, which is just unit, you also get this resumption. And that represents the rest of the computation that you're handling. So what happens now? Well, we just continue, but we stick the resumption of the current thread on the end of the queue. And that's it. That's a very concise implementation of concurrency. And we can implement all kinds of other effects here. This is just one example. I should say this is I've done this using a shallow version of handlers. So the resumption here, the handler is not automatically being wrapped around the resumption here. I've had to use the general recursion of the programming language in order to keep going around. That was just because it's a bit more simpler. It's a bit simpler to present that on a single slide, but I'm actually going to switch to deep handlers later. So if we run this, then it interleaves as expected. So okay, anyway, there's effect handlers. Now I'm going to move on to the actual calculus. So handler calculus. So as with many of the systems you've already seen today, actually we have a separation between values and computations, and that appears at the type level as well as elsewhere. We need something to get going. An empty type is what I'm providing. And then we also have a type of handlers. So this says this type takes a computation C of type C and handles it using a computation of type D. And well, what is a computation type? It returns a value, but it also has an effect. And an effect is just given by a signature of operations. I've chosen to make my operations n-ary here, which gives an easy way of encoding products. Okay, so fairly simple set of types there. And then we have the terms. And the only kind of value terms we have are variables and handlers. And a handler consists of a return clause and a collection of operation clauses, like you saw in the example. So because we have the empty type, we also have an elimination form, absurd, for the empty type. I've chosen to include return and let because it's nicer, but you could, in theory, well, no, you definitely can get rid of these technically if you want. And in fact, you can get rid of return clauses if you want, because you can encode those as exception operations. But then we have operations and we have handling of computations. But notice that this thing here is a general value because the handlers are first-class values themselves. Here's some typing rules. You don't need to look at all of the details. Crucial thing is we have a judgment for values and a judgment for computations. Variables are standard, absurd is pretty standard, and return and let are as well. You see the effects in let have to be the same in both components. When we have an operation, it needs to be in the effect of the computation type. And then handling is like a form of application. And the complicated one is the handler rule, but it's basically just what you'd expect. I guess the important point is that this is a deep handler, which means the return type of this resumption here is the final computation type D here, which means that the handler is automatically wrapping itself around. I mean, we will see that here in the operational semantics, which again is pretty standard. So we have a standard rule for let. If you have a return inside a let, you just do a substitution, and then for the return clause of a handler, you have a very similar rule. And this kind of hints at why, well, you don't really need let if you want to get rid of it, but it's that you end up with a more compositional system if you do keep let and return. So here, yeah, it's just substituting the value in the return clause, and then for operations, you capture the context up to the the nearest handle. And crucially, we wrap the handler again around the context. So this is deep. Okay, so this is this basic calculus. I don't think it shouldn't be very controversial, hopefully. Now what I'm going to show you is just how we encode lots of different things in this. So first of all, some syntactic sugar. So we can just talk about a pure type by just a pure type is just one that doesn't have any effects, and we can omit those effects in that case. The unit type we can do as a handler that goes from pure empty to pure empty. We can do thunks then. It's often going to be convenient with my encodings to use the empty type. So we're basically going to use the effect structure to encode data types. So I'll just omit the 0 in that case. Similarly, we might actually have operations that don't return a value. So these are basically like exceptions. And then in which case I just won't write the 0. The pure handler that returns a value of empty, pure handler of an empty type computation is quite convenient to use sometimes. I'll just write bottom for that. And then this is for exception handlers where we don't need the resumption. I don't bother writing the resumption if you don't need it. So as I said, this is all kind of coming from this view of computations as trees. So if you're familiar with the free monad kind of encoding, then it's not that surprising that we're going to be able to encode data types here. And in particular, if you imagine, if you've got this functor here, if we instantiate a to 0, then essentially we're just taking the fixed point of a functor. So first of all, let's start with functions. We can just, if we have pure no effects, then well, we've got a function. So that we've already got something like a function type. We might want to do effectful functions where we actually have a pure computation where we're handling and we produce some computation with effects. And then Lambda is just a pure handler with a return clause and nothing else. An application is just where we handle that. Okay. Unit, I already mentioned, we can do that as a handler going from 0 to 0, and then just the identity handler. Although actually we could have chosen the bottom handler as well. That would have worked just as well. Products, our operations are n-ary, so we can just encode them by using a pair operation. And here's the sort of pattern you'll see cropping up over and over again. We're encoding our data type as a thunk, where inside that thunk we run the pair operation here. That builds a pair, and then to deconstruct it, I've chosen to do it with this let sort of pattern matching elimination form here. We just handle that thunk. And yeah, you have the bottom clause because here there's an implicit 0. And that should be straightforward. We get sums kind of for free from the operation structure here. So you can just have injection operations and then the elimination using the case. We have the different clauses for the two injections. But we can also do more interesting things, and this is taking advantage of the fact that this is a deep handler that is effectively building in a form of fold or primitive recursion. So here we have natural numbers. We have the 0 constructor, which we do as a 0 effect. But because 0 is kind of the end of your data type, that's the we actually return 0 here, whereas the successor, it actually returns a unit. So if we want to encode 0, well, it's like that. But if you want to encode the successor, then you actually run successor, and then this is sequential composition here, which is encodable using let. You do suck, and then you continue with the rest of the natural number, and then we can encode a recursor as well. So you have the 0 case and the successor case, and you just handle this natural number computation here. And in the 0 case, you take the 0 case, but in the successor case, you see you get the resumption here, and that's what allows it to keep on going. We can go further. We can do lists, for instance, using the same kind of pattern. And in general, you can encode any data type, any positive data type. But a sort of more direct way of encoding recursive types involves extending our calculus slightly with recursive effects. So, I mean, this is a little bit unsatisfactory because you're suddenly collapsing everything, but it's worth at least considering. So if we add recursive effects to the system, so that's actually useful for. If we took that cooperative concurrency example I had before, we might want to add another operation for forking off new processes, so that we didn't just have a fixed set of cooperative processes. But inside the fork operation, you see you have a thunk, which needs to be able to perform the same effects again. So recursive effects are a thing that's useful. Though there are other ways of doing this that are a little bit more well-behaved, but more complicated in some ways, like scoped effects. But anyway, if we've added these things, then we can just encode recursive data types in a very general way here by adding a roll operation, and then roll just invokes that. So in here you see this effect is recursive, and then unrolling is just matching against the roll operation. A more interesting extension, I think, is making the operations parametric. So this is useful, vaguely useful for doing exception handling, but you can also do much more general examples like general versions of shift and reset. But I'll just illustrate this example. If we have a fail exception here, the idea with an exception is you should be able to invoke it anywhere. Hence, we abstract over this type variable here, and we say rather than it returning a particular type, it can return any type at all. When I sort of originally thought about these things, I was thinking of sort of polymorphic operations and thinking, oh, does that let me encode universals? But it doesn't. And if you think about it, what you've really got here is existential types, because when you have one of these operations, they're abstract. You're providing a pair of the type and the operation. And then here's the encoding you get of existential types. We have a pack operation, and then an existential pair is just obtained by using the pack operation, and the elimination form, which you see kind of matches up with the way in which I did the pair elimination before. That's why I chose that syntax. It is just matching against pack and pulls it apart. And so that's quite nice. And now I'm going to go off on a slight digression. Because I got to this stage in this exercise and I was kind of thinking, well, I know that I can encode existentials using universals. Can I do something the other way around? Can I encode universals using existential so that I don't have to add some extra thing to my calculus? I mean, I'm not sure this is necessarily a good idea, but it was an interesting exercise for me, and it exposed me to some things I hadn't previously really thought about. So first, let's just sort of think about where this encoding might come from. So the usual encoding, you can see it arising from the De Morgan, the classical De Morgan dual of existentials. If there exists an x such that A, then that's the same as not for all x, not A. And then if we expand out the nots, you can stick, so not A becomes A arrow bottom, for instance. Then you see this. But if you're in system F, then you can actually generalize this type by sticking an extra for all around it. And this is really nice because it gives you compositional encodings of universals. Because yeah, once you end up with bottom, you're kind of a bit stuck. But with this type, you can instantiate it with whatever type is necessary. And this is used all over the place. So what happens if we try going the other way? Well, we can still do a De Morgan dual thing here. But you can't generalize. Well, you can try and generalize this type, but then you're introducing another for all, which was the thing we were trying to eliminate. So it doesn't really work. But we're not completely lost here. You can still do an encoding along these lines, and it is essentially a CPS encoding. The disadvantage versus this other system F1 is it's going to be a global transformation you're going to have to do on your program. You're going to have to turn everything into CPS, and you're going to get some final result type. And when I looked into this, I realized that there's some nice work by Fujita, who worked out a very minimal CPS translation, just for a very minimal, well, what we call minimal existential logic, where we have bottom, we have negation, which you can think of as functions that don't return a value. We have products and existentials, but you don't have anything else. And what's rather cool about this is you can encode the whole of system F in this language. Yeah, so this is the language. So you have lambdas, but this M here must have type bottom. And this is basically his translation. So it's worth looking to understand it. I think it's best to look at the translation on judgments, because you see that the context actually gets negated. The variables that appear in the context because they start off as value variables, but they turn into continuation variables. And also the returned value is also a continuation. This allows him to translate X to itself. But I guess I'm not going to go through the details of this, but I'm just going to say it's nice and simple. So okay, this kind of works, but how do I fit that into my setting? And this is something I've not actually fully worked out. But one way we can deal with this is if we wanted to take the handler calculus with parametric operations, and then we want to add universals, we can actually just compose two CPS translations together, because we can give a CPS translation for the handler calculus I gave, and then compose that with this translation. And CPS translation goes into system F. Again, I'm not sure I want to go through all of the. Yeah, I definitely don't want to go through all the details of this, but I'm just telling you that this is a relatively routine exercise, and it just works out reasonably well. And these are the definitions. I guess the key thing is that you have computations in this effectful calculus end up being represented as pairs of continuations and dispatches that tell you how to implement the operations. And it scales to deal with the existentials that we get from the parametric operations. So I'm going to finish up here with a couple of questions that I haven't properly thought about yet, or I have thought about, but I haven't worked out the details of. So adding effect polymorphisms to this is probably essential, but it makes the picture more complicated. You need something more than systemf, I think, if you want to do the CPS translation. And then the other thing, as I sort of alluded to earlier, this question is a nice kind of compositional translation of universals into a minimal parametric handler calculus, so that I don't actually have to do this very monolithic thing. But that's something for future work. Anyway, that's it for me. So thanks. Any more questions?
Okay, thank you. Right. There are actually a couple of questions on Q&A. Can you see them, by the way, or I have to read them?
I think I can see them. So Yotam there says, "What do you mean by getting a more compositional system? If you keep let." Let's see. So I mean, part of it. Actually, maybe let's not so problematic. I like starting off from this very minimal calculus where you only have let and return, and you don't have anything higher order at all. That we can encode it with this more sophisticated system. It's not too harmful, but it doesn't feel quite right. I think if you try to decompose various denotational semantics, it might become more apparent. The other thing of being able to encode return, that really does get in the way of computation if you encode return as composition of computations if you encode return as an exception. So anyway, I don't know whether that answers your question, but feel free to ask me more about that later if you want. The next question, Kenichi Asai, how do you find the matching handler in OP of the small step semantics? I don't know what that means.
I think it probably your rule for the handler, so in operational semantics for your handlers. So when operation does not matches, or the handler
it does not match. Yes, sorry. In my for calculus, the type system is going to ensure that you have to give complete handlers, so it must match.
Okay.
So I kind of simplified things there. This is another. There are other extensions that are important here in practice, like effect forwarding, where you have to do something more complicated. It's a constant time search because the immediately enclosing handler must be there, because the handler has to handle all operations.
Okay.
So this is the same as in the original presentation of handlers that Gordon and Mattia gave.
Okay. Well, it's all the time. Unfortunately, I also have questions, but I'll ask you later. Well, thank you again for the presentation. Well, we'll continue some other time, but now it's the last speaker of the session, Yotam Dvir. He would present his joint work with other people. And can you share the screen? Or you have the video?
I'm trying to share the screen. Just a moment. Do you see it?
Okay. Yes, I can see it.
Okay, very good. So, hi everybody. My name is Yotam, and I'll be presenting our work on developing a monad for a shared state. And this is joint work with Toad Kamar and Nuri Lav. So I hope you see the slide numbers on the bottom right, in case you need to reference them. Okay. So in this talk, we will discuss a particular way to find contextually equivalent programs using algebraic effects. And we will follow this general roadmap you see here. So first we define an equational theory, operations and equational axioms over them. So for example, this UU last axiom from the theory of global state. If you update the value in location X, and then you update it again, you can just get rid of the first update because you override it with the second one. So in general, every equational theory induces a monad, which encapsulates the theory. It's useful to find a representation of this monad that's intuitive. So for example, for the theory of global state, the elements of the monad take an initial state and give back a return value and the final state. Once you have this, you define denotations. This step is mostly obvious given that we already have defined our equational theory and operations. We had these denotations already somewhere in our mind. So you can see here, for example, this denotation of this program in two ways. One as interpretation of the operations, the lookup operation, an update operation, and in another more explicit way as a function that takes an initial state and returns a pair. Finally, if everything was done correctly, denotations should agree with the operational semantics. So if two programs have the same denotation, then they have the same operational behavior within any context. And this quantification over all contexts is what makes the adequacy theorem useful and powerful. So in this talk, we will look into how this could play out in the concurrent setting. So we'll first review what happens in global state and then dive into the difficulties that arise when considering shared state. Okay, so let's review global state. You can see in this slide denotations of two programs with effects. And there's this chain of global state equations that show these denotations are equal. So, for example, one of these equations is the UU last equation that we saw before that allows us to eliminate this update. And thanks to a known adequacy theorem for global state, if anyone knows what I should cite here, let me know later. But we have adequacy for global state. If denotations are equal, then they have the same operational semantics in any context. Just to give an example, consider this context of running the program and then looking up X. And you can see from this particular state, for example, they have the same operational semantics. They end up in the same state and return 1. Right, you're overriding X with Y and then overriding it with Z, so it gets back to 1. Okay, so where did the equations that we used come from? They come from the global state theory, which is due to Plotkin power. So here we have the axioms. The first three have to do with single state interactions. We already saw UU last. There's also UL determine, which says if I update X to U and then I look up X and continue accordingly, then I already know what I'm going to continue with. I know what the value I'm looking up will be because I just updated it. So this equation states that. And there's also LU no up, which says that if I look up X and then update X to the value I just found and continue independently of what I looked up, then I can just continue without these lookup and update. There are also, the other equations have to do with interactions with, that there is essentially no interaction between different locations. If I look up X and then update Y, I could just update Y and then look up X if X and Y are different. And we list a few notable consequences here, which help us find normal forms for these algebraic terms in the theory. So for example, these two final equations here help us make sure that there is exactly one lookup for each location. Right? Because if I have 2, I can eliminate 1. And if I don't have any, I can add 1. And just as an aside, this equation used to be, originally was one of the axioms, but it was later proven to be a consequence of them. Okay, so moving on to the definition of the monad, right? We defined the equational theory. Now we're defining the monad. And the monad is going to be inspired by the normal form. So as an example, let's take this term, looking up z, and then updating x to what we found, and returning the unit. Using the equations, we can show that this is equal to this term. We look up each location exactly once in order, and then update each location once in order, and then return something. So the idea is that the lookups fetch the state, and then the updates determine what the final state will be. Okay, and this is how we come up with this intuitive set as the carrier. And the interpretations are also rather intuitive. For example, updating. What does update mean? It means that we take the initial state, update it according to what's written here, and then plugging it into the continuation. To the continuation t here. Okay, and what we get is this representation theorem for global state. So in general, a model for an equational theory is a carrier and interpretations that satisfy the equations. And a model on an arbitrary set comes also with a return function, which you can also think of as pure, a monadic pure, which relates the arbitrary set with the carrier. And the model is free. It means that essentially it doesn't have any more information than what the equations demand. There's a precise definition that I won't reiterate here. And once we have this model, we get bind automatically. So we have the carrier, we have return, and thanks to properties that bind has to satisfy in relation to these interpretations, bind is given for free. And note that we'll use this notation for the rest of the talk. Okay, so all of this was global state. Now let's look into shared state and see what changes. So we want an adequacy theorem for shared state. It looks exactly the same, but the programs are different, right? And it's no surprise that something will go bad. So consider this context where we run M in parallel to looking up X. And if we consider the two programs from before, one possible run we could start with this state, with this program, is X being looked up in between these two commands. So X will be 0 when it's being looked up. And there's no way for X to be 0 when it's being looked up in this program. So there's a context in which they behave differently, and so the denotations can't be equal. Otherwise, we won't have adequacy. So we have to let go of something from the original global state setting, either invalidate one of the equations we used or change how denotations are defined. And the second option is what we'll do. We're going to keep the equations, the global state equations, but we're going to add new operations and change the denotations, where the operations will help us take the environment into consideration. So, for example, here, we're going to be explicit about something happening between updating X and looking up Z, just as it was here. But we'll see this, and we'll see this soon. Okay. So just to review, this is the roadmap that we're following. We need to define an equational theory, then a monad will be induced, but we'll find an intuitive representation for the monad. We'll define denotations, and finally, we hope that adequacy follows, but this is still a work in progress. We've advanced toward this goal, but we still haven't reached it. Okay, so let's start with the operations. So we're keeping lookup and update, but we're adding new operations to reflect the meaning of programs in the concurrent setting. So we're adding an expose operator. Expose X means that another thread did lookup X. Okay, note that expose doesn't bind a value. We have interference, which means another thread did an update of this location to this value. And we also add an operator for choice, non-deterministic choice, because concurrent programs are inherently non-deterministic, the choice of which thread should run. And we're also going to introduce this shorthand. of intervening effects. So there's a sum here. We're choosing any choice of any sequence of i's and e's is going to be part of this. And now we can see how we define the denotations. They're just like before, a lookup and an update, but we're putting these intervening effects before and after every local effect. So this is us being explicit about the fact that someone can intervene in between. And we will see if we have time that denotations turn out not to be equal, which is what we wanted, because again, if they were equal, then we'd have a counterexample to adequacy. And because we know there's a context in which they don't run the same. So we're done with the operations. Let's look at the equations. As we said, we are retaining the equations from before, global state. And we also have these single location axioms. I ill determine, same reasoning as you ill determine. If someone else updated x to u and then I look up x, I know what I'm going to find. No, the point is that someone else updated x to u just before I looked it up. So I really do know what the value will be. There's I last, which is analogous to UU last. And the second right overwrites the first one. And there's EE idempotency, which means that we only care if a value was exposed. It doesn't matter how many times the same value was exposed if it was done in a row, consecutively. We also state that different locations commute, though in particular, lookup and expose commute even in the same location, because when I look up or someone else looks up, the state doesn't change. So it doesn't matter in which order this happens. And we also include the standard non-deterministic theory so that the sum operator really does behave like a non-deterministic choice. And we say that non-determinism and other operators commute as well. Again, we have these notable consequences, which help us find the normal form later on. Let's look at the first one. If the environment did this interference, changing x to u, to v, sorry, and then I change x to v, then I can forget about me changing x to v because the environment already did that. And there are subtle points here. Why do I need to remember that the environment is updated x to v? Why not remember that I updated x to v? Okay, but here I don't really need to justify this equation because it's a consequence of the other equations. Right? But again, it's subtle. So let's look at some equations that aren't consequences of the axioms. The first one is the most important, I think, on this slide. So let's focus on that one. We have, if we have an update and then an update before an interference, why not again remove the update? Okay, so it's very similar to what we had before, where we remove the update after someone else updated the same thing. Why not also eliminate the update before? So the problem is that if we have these two together, it implies out of thin air behavior. So to see this precisely, you need to go into the details of how synchronization is defined, and we still haven't shown this. But hopefully you'll believe me that what happens is that if you have two programs that do nothing in parallel, they somehow should be able to update the state if you have these equations, and you want adequacy. So obviously we don't want this to happen because we don't have a rule that updates the state from programs that don't do anything. Okay, so this equation is bad. We shouldn't include it. Another option is the equation that's analogous to LU no up, but with I instead of U. And it's the only U versus I global state analog that we haven't included. We thought that it implies that I and U are equal, but that was a miscalculation. So we're still looking into maybe we should include this equation. So if you have any thoughts about this, I'd be very glad to hear. Okay, so considering time, I won't go over the last one, but maybe later if you want to ask about it. Okay, so now that we've gone over the equational theory, next up, the monad. Okay. So let's think about global state. Let's compare it. So in global state, we had functions that take state, right? So this remains the same. But the difference now, one of the two differences is that we're returning a set of pairs. Okay? And this set, the idea is that it's the non-deterministic choices that we can make. Another difference is that the pair is the return value, and instead of states, we have histories. Histories are maps from locations to chronicles instead of values, where the idea is that chronicles don't just keep track of the values, they keep track of all the intervening effects that, at least semantically, all the intervening effects that happened. And not only that, they do so, they only allow certain sequences of these U, I, and E. It's a bit of an arbitrary choice which sequences to include and which not. The point is that you need to make sure that there is uniqueness so that the model will be free. And then we end up with a free model. So there are some rules here about what makes things that make sure that the sequence is unique. I won't go over this exactly, but just to provide one example, this here, the second one on the list, is not a chronicle because one of the rules says that we need a U after every I and every E. And we don't have a U here, right? After this I. There is also an example of a history here. You see a map from locations to chronicles, and even an example of an element of the monad, in particular at the unit set. Okay, indeed, it takes a state, it returns a set, in this case, a singleton set with a pair, where there's the unit, which is in the set, so that's good, and a history. Okay, we're still defining the monad. We need interpretations of the operators. So lookup and update remain the same, essentially the same, though there are different kind of objects now, but it looks like the same formula. And E and I add their respective interference to the chronicle. Okay, for example, expose X exposes at X, this is this map X here, and adds E to the chronicle at X. Okay, so so this is an operator that I'm not defining on the slides. Okay, but the notation is suggestive. Okay, so we can't just add an E to the chronicle, otherwise we get a sequence which isn't the chronicle, right? Because chronicles always start with a U. So what we do is we add this like no op like U. See, it updates the state to what the state already was at X. So this U, the meaning of this U is don't really do anything. And so this is kind of a technical detail. And the interpretation of the sum operation is just collecting all the choice options in a union. So I've included an example of a calculation. I won't go over it entirely, just note that it looks like the term from before, only we have this E in the middle that I said we'll be explicit about. And once we plug in a state, we end up with a set of pairs. And this chronicle at X indeed does have an expose in it. Okay, so with these interpretations that we saw before and the set we saw before, we have a free shared state model on X, right? And this is the return function. Again, it's kind of trivial. It takes a state and returns a singleton with, okay, so it's only one pair. It's the thing that we plugged into return, and this is a trivial history. Takes the location and then updates to what the state already said about that location, and no intervening effects. Okay, so now we define the denotational semantics. Most of them are standard. Okay, 30-year-old standard here. The only difference is what we do with the programs with effects. And again, the difference is rather small. all we do is we plug in these intervening effects before and after each local effect. You see here and here. We still haven't defined concurrency, the denotations of running two programs in parallel, and we'll do that soon. So this is the example. I don't have time to go into it, so I'll just skip. If you want to, in the Q&A or later, I can go over it. Okay, so now let's define the denotations of synchronization. This is the most crucial piece, right? And the challenge is, hey, when we in general denotations, the point is that you take a program and you calculate the denotation of the larger program recursively in terms of the denotation of the parts. So we need to somehow define this using the denotation of M and N. So this is the challenge of moving between the semantics back and forth. Okay, we'll see this. We'll see this now using an example. So we want to see what happens where this plays the role of M and this plays the role of N. Right? It's like the example we saw before. This was the program and this was the context here. Okay, what we do is, first of all, we're looking at it state by state. And that's one key thing that took us a while to think about, is when we want to synchronize stuff, we pick a particular state and only sync it at that particular state. And the other thing is always to, right, this is non-deterministic. We don't know which intervening effects will happen and which won't. So we only take one option. You see with this E here, we only take one option from here. Okay, there is no sum operator in either of these. And we sync up deterministic terms. And then collecting all of these synchronizations of deterministic terms, we get all of the options for the concurrency here. So let's go over the synchronizations. You can already see that this kind of matches up. You have L and E, you have U and I, E and L, etc. But you need to make sure that what happens with the state actually matches up. So lookup and expose, together what happens is a lookup. What's Y here? Y here is 0. So when we continue the synchronization, we set this U to 0. And thankfully now it matches the I x0. So this synchronizes to UX0, which updates the state. And now we need to continue the synchronization where X is 0. And so forth and so forth and so on. This thankfully works out. And once we get to the values, we just we ignore the state. It's all okay. And we just return the pair. And now we got a term, an algebraic term, which once we interpret it, we'll get an element of the monad, which will include here at this particular state. Okay, this is what I wrote here. I wrote the interpretation of what we have here at this particular state is part of the denotation of the parallel execution. So this is the formal definition where this entire thing in notation is this. So I didn't write the formal definition, but again, if you want to ask me about this later, I can show you. Okay, so we don't have the adequacy theorem, but we do have the soundness theorem, assuming M is closed. If it runs a single step, it doesn't add new options. It can only eliminate some of its non-deterministic options from the denotation. And so it's a stepping stone to adequacy. So that's what we have so far. So in conclusion, we've defined an algebraic theory for shared state. We've proven a representation theorem, an explicit definition of the free model as a monad. And we've proven a soundness theorem. And hopefully we can use this soundness theorem and some kind of definition of a logical relation to prove adequacy. We also have other things that we plan for the farther future. And that's it. So thank you very much.
Much for the presentation. There are a few questions, but I think Ohad has answered almost all of them, or all of them.
Useful odds. Thank you.
Yes, useful to have a quarter.
Yeah.
Who is present, right? So you don't. So for others, I mean, please see the discussion in the chat because there is already, I mean, long discussion about this and long comments, and I think that he answered all of those things.
Okay.
Yes. So
Okay.
as Asa said, that weak memory models is the most interesting things. How you can
Yeah.
maybe what my question, not a question, but a comment that adequacy. Yes, of course, it's. I mean, the kind of uneasiness about adequacy that you need to have operational semantics. So now you need to have not only the notational semantics but the operational semantics.
Oh, excuse me, because I didn't actually include it in the slide, but we do have operational semantics.
Yeah, so
I mean,
that's
the sounded theorem is in terms of the operational semantics. So yeah, we do have operational semantics, but they're just the usual sequential concurrency semantics where everything is. We're using specifically call by value, but that's not the important point. We could also have used call by name or anything similar. I don't think that would affect adequacy in any way. What is very important is that our operational semantics for concurrency are the most trivial ones, one with sequential concurrency, and handling weak memory models will complicate this very much, I think, but that's for the future. Yeah.
But my comment about this, that there is a different version of adequacy, purely denotational, right? You can show the semantics that denotational semantics is adequate if there is two expressions which have equal denotation, then putting in context, arbitrary context, that make it a complete program, also makes the denotations equal.
I think that's immediate from if you define denotations recursively, I think that's immediate. So
which is actually much easier to deal with this.
Again, I don't think it's. I would call it like a simple proposition. If you define the denotations as we have.
At least in some other people. Peter Moses, for example, that's how he defines adequacy of denotation semantics.
For me, that's a weird definition because I'm only familiar with denotations that are defined recursively. I thought that was part of the point of denotations, but if it's a broader
so in that case, it's adequacy. Well, it means the semantics is gives the correct denotation for the whole program.
Mm-hmm. Okay, so anyway, we mean this the adequacy, not the other one.
Mean for the operational semantics, so it's kind of on a Plotkin standard way where you say that operational semantics and denotation semantics correspond.
Okay. Should I try to answer the other questions here?
I think that it seems.
I can also answer them later. I don't know.
Andrew Hirsch. So, adequacy. Have you thought about preservation of hyperproperties?
I'm sorry. Maybe Ohad can answer because I don't know what that means.
Okay. Well, it's. I don't know. There's a. I don't know. Ohad answered most of them. So okay.
Okay.
Thank you very much again. And so this concludes the session, and we resume after the break and after the long. After the very long break. So it would be. My time would be 11:30, and Korean time is probably would be 10:30. So in 2 hours. So resume in 2 hours. Okay, thank you very much. So see you again in 2 hours. Ohad, can you click on the right button?
Oops. Final session for this year is about to start. Excellent. people are starting to join. Is my audio okay, or should I switch microphones to something closer?
No, your audio is okay.
Okay, thanks. I ran out of batteries on my other phone. Right, so maybe a few logistics. This is the final session for Hope this year. If you've just joined us because the sun has risen in your part of the world, you can ask questions on the Q&A, and if you say that question is private, I will not display it on the screen with your name. I will just read out the question. Otherwise, we'll display your name on the screen with your question. Another option you have is you can raise your hand, and then we'll bring you onto the stage at the end of the talk. So the Q&A session, so you can ask your question live, or you can ask questions in the chat and talk to the other participants in the room. Yeah, we are currently live streaming on YouTube. So if you're speaking, take note of that, because you'll be live streamed as you speak. And without further ado, I will start the first talk of this session by naming you and Dan on first-class names for effect handlers.
Welcome to our talk on named effect handlers. This work is in collaboration with Ningning and Dan, who will show up later in this video. So let me begin with a quick recap of effect handlers. Effect handlers are a generalization of exception handlers where the user can resume the computation surrounding an effect operation. Here's an example written in the Coca programming language. We are defining a new effect, read, that has a single operation, ask. In the handler, we define the interpretation of the ask operation as 1. We do this by passing 1 to the resume function, which represents the continuation surrounding the call to ask. In Coca, we can actually write this program in a more concise way using the read syntax. By writing read handler action, we can evaluate the action under the scope of the handler. As you might have learned from the talks given earlier today, the effect handlers can express a wide range of computational effects, and they have industrial applications as well. Compared with other approaches to expressing effects, effect handlers are more composable. In other words, using effect handlers, it is easy to program with different kinds of effects. For instance, if we wish to perform the read and exception effects in a computation, we simply wrap that computation around 2 handlers, one for read and the other for exceptions. However, plain effect handlers are not convenient when we have multiple instances of the same effect. Suppose we have 2 handlers of the read effect and call the ask operation twice. Since operations are by default handled by the innermost handler, both calls to the ask operation are interpreted as 1. But what if we wish the second ask to be handled by the outer handler? One possible workaround is to use masking. For instance, if we mask the effect of the second ask operation, we can skip the inner handler and obtain the expected result. This technique is available in several effect handler languages, such as Frank and Coca. However, programming with masking is cumbersome and non-scalable because it requires us to know what handlers are surrounding each computation. In some sense, it is like programming with the wrong indices, which we certainly don't want to do. What we want is a mechanism that allows us to refer to handlers by name, that is, a named variant of effect handlers. Here, we name the inner handler H1 and the outer handler H2. Then in the action, we can easily choose the right handler for each call to the ask operation. This is convenient, but unfortunately, name handlers pose a challenge to the soundness of the language. So let's look at this program. We have two handlers for the read effect named H1 and H2. Under these handlers, we create an anonymous function that performs the ask operation on H1. At runtime, the inner handler returns this anonymous function, and as a result, the handler name H1 escapes its handler scope. So if we call the return function, we will get stuck because there will be no handler with name H1 surrounding the ask operation. The problem of name escaping has been discussed by two recent studies. Their solution is twofold. First, they treat handler names as second-class values. This means handler names cannot be returned from a function or put in a date structure or stored in a mutable state. Second, they mention handler names in the type of expressions. So their type system looks like a dependent or region type system. With these design decisions, they were able to build a sound calculus where handler names can never escape. In this talk, we are going to show you a different approach to the name escaping problem. Specifically, we treat handler names as first-class values and prevent their escaping through the standard rank 2 polymorphism. In the rest of this talk, we first demonstrate two applications of named handlers. We then explain how to statically prevent the escaping of handler names. And lastly, we briefly talk about our Coca implementation of named handlers. Okay, let's start with the applications of named handlers. Our first application is file handling. Here's the signature of the file effect. The effect has one operation called readLine, which receives no argument and returns a string. The interpretation of readLine is defined as the file function. The function takes in a file name fname and an action. Given these arguments, the file function stores the content of the file using a library function provided by Coca. It then creates a handler named f and runs the action by passing f to the action. When the readLine operation is called during the evaluation of the action, it is interpreted as the first line of the file or an empty string. Having implemented a handler, we define a helper function, catlines, that receives a tuple of files and concatenates their first lines. And in the main function, we create two file handlers named f1 and f2 and pass these names to the catlines function. An important observation here is that we are using the name of file handlers as first-class values. More precisely, we put the names f1 and f2 in a tuple and pass this tuple to catlines. This is impossible in the existing calculi of named handlers, where names are second class. All right, now we move on to the second application, which is heap references. Again, we start by declaring a new effect called ref, which has two operations, get and set. For simplicity, we assume reference cells can only hold integer values, but it is easy to implement polymorphic references. After declaring the ref effect, we define the readRef function as the handler of the ref effect. Here we are using Coca's primitive state, which is itself implemented as an effect handler. The definition of readRef is straightforward. We initialize the reference cell to the given initial value and interpret get and set in the standard way. That is, get returns the current value of the reference cell and set updates the value to the given argument. In the main function, we create two ref handlers and use their names R1 and R2 as references. This program works as expected, but the way we create references is a bit different from what we do in a language with native support for references. The reason is that we have to statically instantiate necessary handlers at implementation time. This is not only inconvenient, but also less expressive. Suppose we have a function escape, which creates a reference R and immediately returns it. If we accept this program, we would let the name R escape its handler scope and get a runtime error due to the absence of the matching handlers. So can we realize regular dynamic references using effect handlers? I'll leave this question to Dan.
Thank you, Yu, for the nice introduction. In this section, I will show how we can express dynamic named handlers, where we can, for example, dynamically create an arbitrary amount of references and return them from deep inside the call stack. To understand how this works, we first take a short detour into non-tail resumptive handlers. Such handlers do not only capture the context under the handler, but also change the context right above them. Let's look at a tick example here that leaves a 1+ on the stack when resuming. When we start, the tick handler is on the stack and we perform a tick operation. And this will capture the entire context as a resumption. When we resume, the 1+ though stays on the stack and we just keep evaluating from here on, and when the next tick is performed, the same happens, and again there will be a 1+ just above the handler frame. Eventually, when we keep evaluating, we will end up with 3 as the final result. We're going to use the same trick for dynamic named handlers, but instead of the 1+ frames, we put a named handler there. We use the withref handler again as is, which is just a regular named handler. But also, we use a regular static effect handler, heap, under which all reference operations are scoped. We call this heap effect the umbrella effect. In particular, we pass the resume as the action for withref, effectively pushing all named handlers just above the heap handler in the evaluation context. Let's see how that works for the previous escape example. Here is our previous escape example, but now with the heap handler. We start this time with the heap handler already in the context and perform a regular new ref operation to create R1. This yields to the heap handler that captures the entire context again as a resumption, including the umbrella heap handler itself. When withref is executed, the fresh named handler for the reference is installed. And then, when we resume, the ref handler will be right above the umbrella heap effect, just like in our tick example. And the same happens for the second reference, which is also pushed right above the heap handler. And of course, this can create an arbitrary number of references within the scope of the heap handler. These references can now be returned from escape as is, since they're no longer under a direct handler, but instead just returned from the new ref operation. This is a beautiful interaction between named handlers and regular umbrella handlers to kind of allow them to be installed at the scope of the original umbrella handler, no matter how deep you are in the evaluation context. Moreover, it's just effect handler rules without any further special semantic rules for state or something. Since we can now express local polymorphic heaps this way, it is very expressive, and we believe that this technique can be used to express many other kinds of dynamic resources besides heaps. We can even ensure statically that these references now don't escape the heap they belong to, and Ning Ning will show us how.
Thanks, Ilya and Dan, for your great explanations. Now we move to part 2 of this presentation, formalizing named handlers. Having named handlers as first-class value is convenient, but it is also dangerous, as names can escape the scope of their handlers. For example, the program on the right will raise a runtime error as it fails to find the handler h1 during evaluation. The key observation is that h1 is captured by the anonymous function, which is returned from the function f. But when we call this function after we return from f, the handler h1 will no longer be available in the evaluation context. We are going to guarantee well-scopeedness of handler names using rank 2 polymorphic types, which is a well-understood technique used by, for example, Haskell's runSt monad. Consider the type signature used by runSt in Haskell, which says that for all result type A, if the first argument to runSt is an st monad that is polymorphic over the state S, then the result is of type A. As the argument is polymorphic over the state S, runSt ensures that the state is internal to the computation and it will never escape. With such a type signature, the program below should be rejected, as the state it uses is not internal to the computation. Fortunately, GHC is able to reject this program with a type error. To see how GHC does this and why this program is ill-typed, let's look at the type of read var v. As v is a mutable variable of state S and value bool, read var v is an st monad with state S and value bool. But the argument of runSt requires a polymorphic type, so we would need to generalize the type of read var v. However, since S is captured in the context, it cannot be generalized, and thus the expression fails to type check. Now we have seen how runSt guarantees well-scopeedness of states. The question is, can we adopt the same idea of rank 2 types to guarantee well-scopeedness of handler names? Our answer is yes. In this slide, we redefine the function read, but this time using rank 2 types for the action. Like before, the argument action to read takes first a handler name, which is like the st monad to runSt. But unlike before, the handler name is scoped by a phantom type variable s, which corresponds to the type variable s in runSt. And importantly, as in runSt, the whole type for action is polymorphic over s. Now we can effectively prevent escaping of handler names, just like how runSt prevents escaping of states. We formalize the idea of ensuring well-scopeedness using rank 2 types as scoped effects, which essentially associate effect labels with a handler scope. Note that scoped effects are an orthogonal idea to named handlers, and the scoped effects themselves can be used to encode interesting applications like safe resource interface. Next, we illustrate the idea of using scoped effects to encode a safe resource interface. Consider we want to define a vector effect, which provides 2 effect operations, push and find. Push adds a new string to the vector and returns its index, while find uses the index to look up the string. We assume the index is an abstract type whose constructor is not exposed. In the handler for vector, we store values of string in the local variable vec, and define push and find using vec. Notice that as we are using scoped effects, the input action has a polymorphic type, which is polymorphic over the scope S. Now it is guaranteed that the lookup in find can never fail at runtime. Namely, the index is always within the bounds of the local list, as each index is uniquely associated with the current handler scope, and we can only use an index returned by push to find elements in the same handler. And whenever we try to use an index we get from one handler to find the index in other handler, we will get a type error, as the scope of the index does not match the scope of the handler. We can rewrite our previous file example using scoped effects. which ensures that files cannot escape its scopes. In Coca, you can define scoped effect using the scoped keyword. In this case, we define the file effect as a named and scoped effect. We can do the same for heap. But the case for heap is more complicated, as we would like to prevent escaping of the named effect ref from the scoped effect heap. To this end, we define heap as a scoped effect, and at the same time, we define ref as a named effect in heap. We call that heap is the umbrella of ref. Note that ref is associated with the scope S from heap S, which are used to associate the references to a particular heap. Now, when we use with ref, the action will take a ref S. All references created by one heap will share the same scope, and so we can, for example, put those references into a list. In summary, in this part, we showed how to guarantee well-scopeness of names using rank2 types as the scoped effects, and we further use scoped effects to guarantee the safety of heaps, which we call umbrella effects. With all these theoretical explanations, you may wonder if everything works well in practice, and Dan is going to tell us more about it.
Thank you, Ningning. The implementation of named handlers using our approach turns out to be actually quite straightforward. We implemented this in the Coca language, which already has rank2 polymorphic type inference, and can therefore directly express most of the type rules using the right primitives. Furthermore, it turns out that the evidence passing transformation that Coca uses for regular effects can directly be used for named handlers as well, and no new runtime mechanisms are required. Tomorrow we give a talk at ICFP about evidence passing in detail, but here we focus on the essence as it applies to named handlers. Coca uses evidence passing in order to efficiently compile effect handlers to plain regular C code. In particular, with evidence passing, we pass down all the handlers and their stack markers in an evidence vector down to each perform operation. Here we denote it as a W. And then the perform can directly select the handler and marker from the evidence vector without needing to search through the stack. And as it turns out, we can just reuse those marker handler tuples as the name of our named handlers. And we pass those names, those tuples, along explicitly now without ever putting them in the evidence vector. As such, a perform on a named handler now gets its handler and marker explicitly in this tuple and doesn't need to select it from the vector. And now there's, since this is already all implemented, there's almost no change in the runtime mechanisms to support named handlers. There's one other interesting implementation aspect. In the paper, we only describe aesthetically checked named effect handlers using rank2 polymorphism, but in our implementation, we offer a choice. We can, of course, use the scoped named handlers and get a static check that the name doesn't escape to the phantom type S here. But also, we can just use a plain named handler, and in that case, we get an exception at runtime if it escapes its scope. And the advantage of the latter, of course, is that it leads to simpler types. You no longer need this extra phantom rank2 S parameter. And since it becomes a runtime exception, it is still sound. Currently, we tend to prefer this in practice, and an exception effect is still fairly benign. For example, even in pure Haskell, any value that's demanded could potentially raise an exception or diverge, and people are generally fine with that. Nevertheless, we're still looking for ways to reduce the annotation burden of the rank2 types and can kind of use static checking more, and any feedback on that would be most welcome. Thank you so much for listening. We hope it was fun. Please try out Coca at cocalang.org, and you can find the named handler examples under the samples directory there. See also our evidence passing talk tomorrow at ICFP, and come to the Coca and FX tutorial on Thursday. Thank you so much.
Thank you. So I see there's a question in the Q&A.
Yes.
Can you infer the rank 2 types of the handle action?
That's a great question. Thank you, Jonathan. So generally, rank 2 type inference is very difficult, as everyone knows, and you generally need to annotate the parameters of functions to allow a kind of inference, right? But Coca is pretty good at propagating that information. So if you write say a handler, then the type of that handler will have a rank 2 type over the action, and that will be pushed down if it can see the action, right? So generally, you don't have to write it, but as soon as you use more abstraction in other functions or something, then you do need to write it, because higher rank type inference just goes beyond Hindley-Milner. I worked hard to make it the burden as low as possible, right?
Thanks. There's Sam. Do you want to go next?
Yeah, thanks. Well, I guess I have lots of questions, but I'll just ask one simple question now. You have these scoped effects. I'm wondering, are they exactly the same thing as the existing things that are called scoped effects, as in the work that people like Nick Wu have done, or are they something different?
No, they're completely unrelated. Oh, sorry, you?
Oh, yeah. I was going to say, yeah, it's not related to that scoped effects.
It might be worth picking a different name then.
Well, yes, but we use kind of scope for the scope of the reference, right? The things are scoped under it.
Yeah.
So, but right. I mean, we are considering though changing the design a bit because the naming, right, is always a bit of a problem. When you have a named handler, you kind of want to refer to a named effect like ref as the reference you're getting as a value, but there's also kind of the effect associated with the references, which now we often use scope for. And we're still looking for maybe there's a better way of doing this. And in the paper, the effect we assign is kind of a ref, and then the actual value we get, we say, I think in the paper we say evidence of ref, to make that more clear.
Okay, can I maybe just have one other question then, relating to what you just said, actually?
Go ahead.
So actually, I was a little bit confused because you mentioned prior work by Biernacki and others, and I think they don't have named handlers, but they rather have named effects. So you can have different instances of the same effect, which is a slightly different thing. I wonder if you've thought about how the two relate. Does this make sense?
We do have named effects, right? Like when I say named handler, I say that that's a handler for a named effect.
Right, but you're associating the name with a particular handler. That's a bit different to having a named effect. You could actually have several different state effects with different names, and you might have several different handlers for those different state effects. Where,
right.
If I understand your design correctly, the name is associated just with the handler.
No, right. What would you? No, you get like.
Yeah, so but it's fixed to a particular handler. If I create a new named handler called foo, then I can only handle the foo version of the effect with the foo handler. Is that not correct?
The foo.
If
I have a name, maybe I misunderstand your question. Right. Sorry. I think if you have a foo effect that's named, right, you can make a named handler and create a new. Maybe foo1, right? And then the effect type will show foo in it. And if I create another named effect handler like foo2, the effect will show in the row like foo, like there's two.
Yeah, this is.
But I mean, maybe.
these are two different things. But yeah, maybe we should continue this discussion online.
Right, but I think an important thing that maybe causes the confusion is like the named handlers the named effects do not show up as such as a type in the effect row, right?
Yeah.
And that's a big difference from the earlier work by Bernacchi, where the names do show up in the effect type, and I think that's what you're getting at, right?
Yes, these are two different mechanisms, and they're not.
They are different. Yes.
Yep.
Absolutely. That's why you also said it's a different approach, and really the goal here is like to treat named handlers as a more first-class entity, right? That we can put, like, say, in a tuple or something, or in a list, and then it's really important that you don't mix like the type level with the value level, as is happening in the other work, right? So we in our work, it's still the type world is very separated from the value world. So you keep that distinction.
My suggestion is that you may well need both of these things ultimately. But anyway.
Oh, maybe, yeah, that may well be true, right?
Thanks.
Yes.
Thanks. We have several questions on the Q&A. Let's start maybe quickly with Max's question. Do you support dynamic generation of named effects? Do you need garbage collection?
Right. So in the heap example, you can see that we could create more and more named handlers, right? An arbitrary number. So how would you get rid of them again, right? In this work, we do not answer the question, right? But indeed, you can imagine like you need to kind of garbage collect handlers from the stack, right? When you see that a reference no longer accessible. That's very interesting. So I want to keep it secret, but there is a way actually where you can explicitly free a reference. I've been looking with you into this. And that is if you have a shallow resumption, you can kind of make a free operation on one of these named reference handlers, and it would remove the handler from the stack using a shallow resumption. So I think that's very interesting, right?
Thanks. And maybe final question while Eli starts to set up. Is a single umbrella effect enough to handle references whose content have different types, or do one need a different umbrella effect for every content type?
No.
So Eli, would you start sharing your screen, please?
Sorry.
Yeah.
So Dan, while you
yes. So to answer the question, yeah, you can use one umbrella effect, like heap, for references that are polymorphic, and you could create, reference of different that hold different types in that single heap. Actually, if you go and download Coca, you can load like sample named handlers heap.kk, and it contains exactly that polymorphic heap example.
Great, thanks. So let's thank all three speakers again. And Eli, if you start sharing your screen, we can lead on to your talk.
Thank you.
Thank you so much.
Thank you. Eli has left the stage. Okay, we're experiencing some technical difficulties. Hopefully, I will be able to resolve them quickly. So I can read out the comment that Jonathan wrote on the Q&A for the benefit of our YouTube viewers. Jonathan says that in effect, where we translate to Kabili, passing named effect are also neatly expressible. And I'm interjecting my own view here that any claim about expressivity has to be very, very carefully phrased, usually with some kind of formal calculus and a formal proof, especially when something is second class. So that's my asterisk for this remark. And Eli?
Systems for partial evaluation of that are integrated with their the weird corners of behavior that they have to support. And so probably it's kind of best to, have some principle of laziness, right? And do as little work as possible. So if you can make the underlying system do the work, then there's no reason to implement something yourself.
Okay, thanks. So James, why don't you start sharing your screen, and let's thank Eli again. Great.
All right, so you see the slides now and tell me what to begin.
Good. Okay. So it's my great pleasure to introduce the final speaker of today, Jimmy Coppell, who has defended his thesis yesterday, right? So congratulations.
Well, 3 days ago, but yes.
2 days ago, sorry. But very recently. Yeah, everyone's clapping. Well done. Welcome, Doctor. And on to you.
Yes, thank you very much for the intro, Hod. So hi, I'm Jimmy. And I'll be talking about some work I did with some colleagues in probabilistic programming, where in the process we discovered something that actually seems pretty important, a bit fundamental to higher order effects. So I was invited to come to this talk to bridge the two communities. So I defended my thesis so recently, I knew I would not be preparing a full 30-minute talk. So that's why I'm going last. So I can go under a bit. Should be a nice reprieve from the usual behavior of talks. And this is estimated about a 17 to 18-minute talk. So let's do it. Okay. Let's play a game. In this game, I'm going to roll a die. And then I want you to predict the die roll. We'll compare. If your prediction is within 1 of the actual die roll, then you win. Otherwise, you lose. Okay, you all have your predictions? Now say you played 2 and you lost. Given that information, how likely would you have been to win had you played 4? So how do we evaluate this? Well, we condition on 2 losing, so we know the die roll couldn't be a 1, 2, or 3. And we win if it's a 4 or 5, and lose if it's a 6, so 2/3. What we just performed there in solving that problem is a counterfactual inference. And the process we use is threefold. First, we'll look at the factual world, what happens. The 2 lost. We abduce what the rolls of the die could have been, 4, 5, or 6. We intervene, do an action on the states, change the guess retroactively to 4, and then predict the winner-loss behavior in this counterfactual world. These kinds of counterfactual inference questions are very common and important in law and in policy. What would have happened had the patient been treated a few minutes earlier? What would have happened if this house was made of a slightly less flammable material when the spark caught? What would have happened had the US stayed in Afghanistan a little bit longer? These are questions we must answer frequently within life, and they have huge consequences. In our ICML paper, we created counterfactual inference as a language feature within a probabilistic programming language. So here's what the die game looks like. And I'm going to walk through this code in detail for a bit, so that I can show you what exactly is special about it from an effects point of view. So here's the code in a version of our Omega language. So first F here, it just takes a random number, compares it to the guess X, returns win or lose. Next, we set the guess at 2 and Y to running the game on this guess. Okay, so what does this last guy do? So we're looking at the value of Y, whether win or lose, but conditioned in the counterfactual world where guess had been set to 4, where in the factual world, Y was observed to actually be a lose. And we sample and draw from here. So there are 3 things going on in this last part, effect-wise. This conditioning and sampling is an ordinary propositive programming language feature. We'll be talking briefly about this in a few minutes for those not familiar. This counterfactual intervention conditioning part is the subject of this talk. So I was called into this project primarily as the most hardcore PL guy to design the semantics. And so I designed the semantics of this counterfactual do operator, and I realized that it was a bit too simple. It must already exist, and it does. Today I'll be showing you how counterfactuals is a combination of laziness and dynamic scope. And as I was discussing with the anonymous reviewers for Hope, I think that there's a lot of ideas that you and the audience can run with from this. So I am going to strive this talk to give you a pretty strong operational understanding so that you might, with a little bit of looking stuff up, be able to run some counterfactual programs by hand. So I'm going to be going pretty slow in parts because I want you to understand none of these ideas are particularly complex, very simple in fact, but there are a couple layers to understand first. So but I'm going to be pausing at points to give you time to digest things. So first, non-directly effect-related simple idea number one, let's talk about the basics of causality. So, what I'm about to show you is pretty much straight out of the Pearl School, especially his book. Not the only way people talk about causality, but it's a very computer science friendly one. Philosophically beautiful, lots of graphs. The object of study in this school of causal inference is the structural causal model, which I like to think of them as straight line programs, which they are. Here's a program. It rains, or doesn't, according to some thing. If there was no rain, then the sprinkler turns on. If there was rain, the sprinkler does not turn on. The grass is wet if either there was rain or a sprinkler. Okay? So let's execute that. So say it doesn't rain, the sprinkler comes on, and whoa, the grass is wet. Amazing. Now let's start to play with this model a bit. So what if we had turned the sprinkler off? So when I ask the question, what happens? Is the grass wet when there's no rain and no sprinkler? So we look at this expression, like, okay, this makes perfect sense. How likely is it to be wet grass when there's no rain and no sprinkler? But that's not what this says. Because conventional probability, this is only defined if you had observed a state in the wild with no rain and no sprinkler. And until we reached and turned the sprinkler off, there are no rain, no sprinkler states, so that condition is a giant division by zero, and this is actually undefined. If you just look at the data, this could be anything. But this makes perfect sense. So we're going to chop that rain to sprinkler edge. Whoosh, there it goes. We'll really get a different model, one in which we basically change align this program to setting sprinkler to false. And we can run this program as normal. Rain off, sprinkler off, grass is not wet. Wow. So we've already stepped outside the bounds of conventional probability theory, conventional statistics. Now we're looking at this funny expression, P of wet grass given not rain and do not sprinkler. That refers to the execution of this alternative intervening model. Here we can see grass is clearly not wet when there's no rain and no sprinkler. That's intervention. And now we have the ingredients to think about counterfactuals. So let's ask the question, if the sprinkler had not come on, would the grass be dry? So here's how that works. You look at the factual world, you see, I told you, the grass was wet and the sprinkler did come on. Those are the observed facts, we condition on them. From that, we can abduce that since the sprinkler turned on, it must not have rained. And so we're going to pull all the non-determinism out of the system. So we'll say whether it rained was actually a deterministic cause of some other factors, call it clouds, call it God, what have you. These are further reduced. Now we know the backgrounds. We can start to look at the counterfactual worlds. In the counterfactual world still does not rain. God makes the same decision, but we say, what if the sprinkler had not come on? So in this counterfactual world, we perform this intervention. And now we can deduce that, indeed, had the sprinkler not come on, the grass would be dry. And that is the abduction, intervention or action, and prediction. Those are the 3 steps of the counterfactual inference. So what we just computed was this weird quantity. P, the grass is wet, given sprinkler came on, comma, do, the sprinkler doesn't come on. Conditioning on sprinkler and do not sprinkler. What is this? It means we observed that actually happens. We deduce other facts we can, and ask what happens had we intervened. So I'm going to pause on this slide for about 45 minutes. I think this is a pretty elegant idea, but sorry, I said 45 minutes. We'll pause here about 45 seconds just to let you stare at this sink in a bit, because we're going to be building on it soon. And if you think you already understand it, then just take a nice 30-second breather. Okay, let's resume. This is starting to sink in. If it's new, counterfactuals are often regarded as mysterious, but this is very beautiful semantics. So I'm going to introduce probabilistic programming. So here, even though I'm using these P's, everything 0, 1, it's deterministic. Let's make it non-deterministic. I'm going to introduce probabilistic programming just long enough to kind of brush it aside. So probabilistic programming, we think of the world has there are many possible worlds. Each of these possible worlds executes and their states evolve. But at certain points, something non-deterministic can happen. And it's like ordinary non-determinism, and the state branches. And the state branches again. But then, here's the rub. You can say, well, this current state seems pretty unlikely, or seems pretty likely. And when change the weights of the current states. In probabilistic programming, then the magic comes when we put this effective computation in a box. We be God looking from the outside and saying, look at these final states. Sample from these worlds based on the likelihood. Give me probabilities, count them. And, well, there's an entire field and conferences about how to do this without enumeration. I'm just going to bring this up. It's actually, even though counterfactual is kind of usually thought as belonging in the world of statistics, probability, the counterfactual stuff I'm going to show you today is mostly orthogonal to this, but the application we know, when you see a twin network being built, just know that usually there is some conditioning and statistical inference involved. So now, let's bring counterfactuals into our programming languages. So we saw how to define a counterfactual for a straight line program by constructing this twin network. I have 2 copies of the model, one real, one which I modified a bit, but they share some background facts. So how do we extend this idea of a twin network to an arbitrary program? So let's look at this program again, and I'm going to split it up into a few parts, talk them independently. F is how the game works, can leave that aside. So we run this y given do of guess 0, 4. What we want to think of is that we are kind of dynamically a twin network. We're copying the previous state in the program. Basically 2 copies of the execution, the factual and counterfactual executions. And
James?
Okay, I'm hearing a weird beep. Yeah?
Yeah. I think your screen is no longer sharing because something happened. Hello, can... Right. But can people hear me? Can someone say in the chat that they can hear me? Yeah, okay, that's great. So, yeah, we can wait a few minutes and
yeah, I think he might be rebooting his computer.
Right. I mean, officially, this is the time the workshop is meant to finish. So I guess if people have pressing issues, they can wrap here. But I see, oh, James, let's see. No, he's disappeared.
Well, I think by the sound, it could be his computer out of charge. So.
Right. Well, we can take advantage of the time to thank the PC, for example, and all the participants. Yep, everyone is clapping. Thank you. Thanks all for making Hope happen this year. Hope hopefully will resume next year as well, right, Oleg?
Yeah.
I won't be in charge, but Oleg will be. And hopefully it will be approved. Hello, James.
Hello. Hi. Yes. So I just refreshed my browser a minute ago.
Fix it. You need to share your screen again if you.
Yes. So. Right now. Or do I need to go back?
I can't see your screen yet. Maybe turn off the video so that, because it says that your connection is not great. So if you turn off the video, maybe that. Oh, okay. Can you hear me?
Yeah. Yes, I hear you.
Okay.
So did you see everything up until the slide?
Yeah, we saw.
Okay, it's just go from here, right?
Yep. But maybe turn off your video just to make sure the connection is more stable.
Okay, I'm doing so.
Thanks. So
all right. So I talked about how I kind of dynamically creating this to a network, copying the previous computation. Now, once we copied everything that happened to this point.
Your screen sharing has disappeared.
Yeah, it's not great.
Program.
James, you just got completely cut off.
So this scales up pretty well. I'm getting a weird beeping again. I'm getting weird beeping. Okay. Every time that happens, little alarms, technical difficulties that I can't see when I'm presenting.
James, we can't see anything.
So we went to this in a real problem programming language called and it can have these counterfactuals, and it's pretty interesting programs. And you do things like for about data pedestrian, determine if I can single frame because the speed costs incredibly lower level semantics. Laziness plus dynamic scope equals counterfactuals. So, and my laziness, I actually need to call my name. We are not going to be memorizing computations. We'll be repeating computations many times, potentially. So let's look at these first few lines. Since this is lazy, of course, the let rule does nothing other than bind a closure. So guess gets balanced to closure empty state, value 2. And then y, we now have a state where it's bound to a closure where guess has been set as before. And when you want, and if you look at this var rule, it's only when you want to use this y are you going to evaluate after the guess. And you're going to do this, and at least in the semantics, every single time you reference y. It's called by name. Now let's add the dynamic scope, and I need a bit more space in my slides. So, okay, move things around a bit. Right, so now let's look at this do part. Well, so here's the rule for do. And basically all the work is done in this retroactive update. Well, what does this retroactive update do? Well, because I've stored the full provenance of y, I've stored the closure, the computation that produced it, and then within that computation, I've stored things like guess, all the variables in there. I can basically just walk the state as a data structure and change guess to 4 everywhere. Bam, bam, guess now 4. And now when I run y, it's giving me the value that it would have been had guess been 4. So that is counterfactual work. So let's compare this briefly to the more classical dynamic scope dlet operator. So look at this program on the left. I'm going to rebind p to 2 before running this function f. So I call it p is 2. Y had been set to p earlier though, so y is 1. And this gives me 3. On the right, I have basically the same program, but I'm using do instead of dlet. This time, I rebound p to 2, but now when I click y, I'm getting the value that y would have been had p been 2. So, 4. So the classical dlet is running computation where I change a variable, whereas do is doing something cooler. It's running this computation with not only that variable rebounds, but kind of gone back in time and changed the provenance, that everything that is data dependent on this changed variable is also updated accordingly. So I've only found one person who's written before about the combination of laziness and dynamic scope, and he basically said it's really complicated, doesn't do what you want it to do, don't combine them. But what we've seen today is that actually laziness and dynamic scope combine beautifully. It's not useless, it's counterfactuals. All right, so hope you all had a great hope, and I'm here for questions.
Thanks. Yeah, there were a few times it got cut out during the last bit. So maybe if you could upload your slides to the web page or link to the paper from the Hope web page, then people would be very happy, because I had some personal requests for that. Yes, people are very happy about that. So I encourage you to upload your slides to the web page, so people can have another look at them afterwards to catch up on the stuff that they missed. Any questions? I can see there's a couple in the chat. Can you say more about why counterfactual inference?
Okay, so questions. Can I say more about why counterfactual inference is useful in programming? All the examples we have so far of counterfactual inference are from probabilistic modeling. So I showed you the example. I showed you the example of the question from a single frame deduce was the driver's speed to cause the crash, and you do that basically by kind of having some variables for driver speed and a model for how fast it can brake and the reaction and whatnot. At the time they see the pedestrian, then you have a program that kind of renders a scene from that. You condition on the actual scene, and then you can ask a counterfactual question, have their speed be slower, would the pedestrian have not been hit? So that's the kind of questions we've been thinking about with counterfactual inference. For peer programming stuff outside of proxy modeling, there are probably uses for it, but we just haven't been thinking in that direction.
So your Tom asked you to show again one of the slides. Maybe he can tell us which one he means.
25 or 26 or 24.
Yeah, I just meant the slide you were just talking about. I think it's one that was cut off, or maybe I'm mistaken. But what the slide with the car that you were just talking about? Which one was it?
Yes, here we are, 22.
Oh, okay. Yeah, this is when you cut back in. Okay, thanks.
Okay. Okay, I suggest we take the rest of this to the social area, to the networking area. And thank Jimmy again. And congratulate him again. Thanks. Claps. And thank you everyone for persisting all the way through Hope. And thank you for making a Hope materialize this year, despite everything. Thanks. That's it. Okay, I'll stop the